We're going to get started. Thank you all for coming to Capstone Day. We are the Neutronomous team. Our slogan is delivering here, there, and everywhere. So before we tell you about our car, we wanted to first introduce ourselves. So I'm Salim Karahan.
I'm Eduardo Lopez. I'm Brian Montoya.
I'm Haldon Wu.
Justice couldn't be here today, unfortunately, due to an emergency, but he was also part of my team.
All right, so, the field of autonomous driving is a very exciting field in electrical engineering, but we mostly see autonomous driving applications in military use or in commercial car manufacturers. And this field isn't without its challenges. Some of the challenges that autonomous cars face are unpredictable road conditions. So there could be other vehicles like bicycles or people like pedestrians walking around and your car might not know what's going on. Sensor interference due to weather. Some sensors don't really work in the daylight. Some sensors don't work in the fog. Rain and snow could also be really difficult, and even just darkness. Autonomous cars are very expensive to manufacture, not only because there's some really high-tech stuff that you're putting on there, but because of the hours and years of research and development and design that goes into making an autonomous car. And lastly, one of the biggest challenges in autonomous driving right now is civilian trust and familiarity. I'm sure you guys have all seen that video of the Tesla hitting those pedestrians, which only happens very rarely, but it's still not something that you want to be associated with a product that you're working on. So for this project, we wanted to sort of create an autonomous car that would tackle these last two challenges, cost and civilian trust and familiarity. And we'll tell you a little bit more about it in the next slide, which is our project objective. So what we wanted to do with this project was to build an autonomous car that can navigate from one location to another on a college campus or in a small town, and it would avoid all dynamic obstacles in its way, and we wanted it to be able to deliver food, packages, and documents.
Basically, starting off on our design layout, here we have some of the major components that we use. Just kind of going through them right here real quick. We use the Arc LiDAR, 3 Raspberry Pis on our car, a BESS, 9 power bank, a very GPS, Imu, and basically the chassis. And I'll talk about it a little bit more in the next slide. So starting off with the chassis, we bought this online. It came with basically the servo motor and the DC motor, 12-volt LiPo battery. Also for the motor, originally for the F110 website, they were using brushless motors, but we're able to only find a brush DC motor. For the speed controller, basically what is this? We call it a BESS. Basically uses pulse width modulation, and you're able to set the speed of the motor due to the duty cycle. Basically, one of the biggest components of our project was the RP LiDAR. This was basically a 2D 360-degree laser scanner. So for those of you that don't know what a LiDAR is, LiDAR basically shoots off a laser beam. As soon as it detects something in its way, it measures the distance back and sends back the information to the Raspberry Pi. Basically, for our project, since we want to use it outdoors, there's a lot of LiDARs that are good indoors, but we needed both indoors and outdoors. So we found this one that works really well outdoors as well. And basically, this LiDAR sends back the information so we can perform something known as SLAM. SLAM is simultaneous localization and mapping that will be discussed later in our presentation.
Another one of our important hardware components was the GPS and Imu unit. We have one that is specifically designed to work with the Raspberry Pi, which is pretty convenient. And the GPS and Imu is pretty important in our project. The main place that we use it is as a feedback element in control systems. So we're measuring angular velocity and the linear acceleration of the car. And we also are using Imu data as a part of the odometry in addition to, or I guess we wanted to use Imu data to help out with the odometry that SLAM does, which we'll talk about more. And then just to give you sort of an overview of all of the hardware working together, this is a system flow diagram that we created. So on the left, we have the sensors that take in information from the outside world. We have the LiDAR sensor that does a laser scan of its surroundings and helps create a map. And then the Imu sensor that picks up information about its acceleration and velocity and orientation and stuff like that. All of that is fed into these 3 Raspberry Pis that we have on our car, which are connected using Wi-Fi. The first Raspberry Pi we call the host Pi, and that sort of does all the sensor transforms, Imu data processing, the 2 PID controllers that we have, and it sends commands out to the motor. The second and third Pi We decided to dedicate those pies to having just one large task to do on their own. So the second pie is doing LiDAR data processing in HectorSlam, which is very computationally heavy, so we have one whole pie devoted to doing that. And the third Raspberry Pi is doing trajectory planning, which we call MoveBase in our project. And again, it's pretty computationally heavy, so we have one whole pie devoted to doing that. And another reason why we chose to use 3 Raspberry Pis in our project is because it sort of made it easier for us to work on the project. We could work on these subsystems at the same time, debug stuff at the same time, and not be held down by one person just using the Pi for one specific task. So that helped us in getting stuff done. And on the last column are the actuators. So back into the real world now, the Raspberry Pi has done all this computation and is sending these commands to the motor, which controls the forward and backward movement of the car, and the servo motor, which controls the steering angle of the car.
Hello. So I'll be talking about the software of our project because our project was mainly software. And firstly, I'll talk about ROS, which stands for Robotics Operating System. And ROS isn't really an operating system, and it's more of a software framework. But it provides us with a lot of useful things. Firstly, it provides us with a communication framework via nodes, topics, and etc., which I'll talk more into in a bit. And it also provides useful tools like interfaces for sensors and mapping. And then it also provides a lot of packages and libraries for useful robotics applications, such as controllers and trajectory plans. And in terms of what ROS we're using ROS Analytics. So in terms of the communication framework of ROS, ROS works with ROS Master, which keeps track of all the nodes and topics and what nodes are subscribed and publishing to what topics. And ROS nodes can kind of be thought of subsystems of the robotic application. This is a nice visual that shows a node publishing a message to a topic, and any node that is subscribed to that topic will receive that message. This helps us kind of separate our system into subsystems and work simultaneously. In terms of our architecture design via ROS, this is what we came up with. Again, we have 3 Raspberry Pis, each kind of have their own responsibilities. Our first Pi, which we call the host Pi, runs ROS Master and kind of has the controller and actuators, which actually moves the vehicle. Pi number 2 is mostly responsible for SLAM, which maps its surroundings. And the SLAM outputs to the cost map topic, which MoveBase on the third Pi is subscribed to, so it can read that cost map. And then also based on photometry, it knows where it is and it can plan the trajectory. MoveBase is a ROS package that we use to actually plan the trajectory, and it gives us command velocities. So we can use that in our control systems, which we call a base controller, to output a control effort. And then using our actuators, we can actually move the vehicle. This is a generated node graph of our system actually running. So once we run everything, ROS can visualize all the nodes and topics. Is kind of what it looks like. Something interesting that you can see is MoveBase, which is a ROS package, is actually made up of even more nodes and topics. But yeah.
Yeah. So what is SLAM? And SLAM has 2 main functions in our project. So one is like mapping the unknown environment. And the second one is like localize the vehicle in our map. We are gonna use this mapping data to do some path planning and obstacle avoidance. Let's talk about the SLAM we use called the Hatter SLAM mapping. This block diagram shows how the Hatter SLAM generate the map. And first, the ArchiLiDAR collects the surrounding environment information and public a topic called scan. And the Hatter SLAM package will subscribe this scan and use that data to create our vehicle map. So when it can move, the Hatter SLAM match the map with the LiDAR scan and try to localize our car and estimate the car pose. Finally, the Hatter SLAM will post the topical map to the MoveBase. Let's move to trajectory planning. The trajectory planning configuration is based on the ROS node called MoveBase. The MoveBase has 4 basic components. 2 cost map and 2 path planner. First, we talk about the global cost map. The global cost map subscribes the map topic, which from the Hatter SLAM. and it will set this map data to the starting map. At the same time, we'll use the ROS visualize tool called RVs to set up the initial point and the goal point. Then the global planner will use the A-star algorithm to create the path from the initial point to the destination. Let's move to the local cost map. The local cost map will subscribe the scans, which from the RP LiDAR. That's a real-time information. So we use that to do some obstacle avoidance, some stuff. And every time when the dynamic obstacle or persons like appear in front of our vehicle, the local planner will create another path, like avoids obstacle and like back to our original path. So finally, the move base like will output a velocity like to the like control system.
Yeah, so just to give a quick overview of the control systems that we implemented in the car, like Leo just said, MoveBase publishes publishes command velocities to the topic, to the command velocity topic, and then our controller node is subscribed to that topic. And basically what it does is it takes in linear velocity and angular velocity as an input from the trajectory planning module, and it compares it to what's actually being measured. So like how quickly the car is actually moving and what angle the car is actually moving at, which we're measuring using the IMU. And then it is fed through these PID gains, which generates a control effort, which in our case is the amount of current we need to either deliver or stop delivering to the motor and the servo to make sure that it's going in the right direction and at the right speed. All right, the next thing is, let me turn the volume down on this one. This is the first demo video that we have. So where we actually got to on this project was we were able to implement most of our subsystems individually and separately. And in the end, the final product that we have is a car that we're able to control using manual commands on a computer that is remote desktop into one of our Raspberry Pis. And what it does while it's moving with manual commands is it maps out its local environment. So you see the LiDAR sensor on there spinning really fast. It's currently generating a map of its local surroundings. And it's using HectorSlam to do that and to localize itself within that map. And on the map, which we'll show you on the next slide, we can select a navigation goal and it will create a trajectory to move to that navigation goal. And so the part of the project, MoveBase, that takes care of the trajectory planning does output command velocities, so angular velocity and linear velocity for the car to get to its desired point. Just make sure the volume is. Yeah. Eduardo, do you want to say something?
So just to clarify again, we were manually controlling it. We had issues actually applying this because of our controller. But this is RViz. This is one of Ross's kind of useful tools to visualize everything. So this is our robot actually moving from the previous video and mapping simultaneously as it moves around. The green path, it's previous path. I don't think we showed it in this video, but we can choose a goal based on this map, and then MoveBase will plan out a path and give command velocities to our controller. But the issues we had with our controller, we weren't able to actually run it.
Oh yeah, good.
And lastly, just with the interest of time, I'll try to go over possible improvements kind of quickly. But as we said, we would preferably try to run everything together. We have all the subsystems working. For example, the IMU data for odometry, we also want to make sure the implementation of state estimation node, which is a ROS package that uses a Pcb filter to give better estimates for the state of the vehicle. Implement those with MoveBase. We implemented that already for the controller, but again, working it together, we weren't able to. And then once we had the controller working, we would want to optimize it because it would work, but then to make it work better, we would kind of tweak the PID parameters and make it more efficient. And then lastly, kind of our boot up sequence, we would like to improve because right now we didn't worry about that. It kind of a long boot up sequence to get everything working. Instead, we would love to write up boot up scripts to kind of have the car working as soon as we turn it on.
Oh, and this last slide, we just wanted to thank Professor Hispania and Professor Reza for their general guidance in this project. Destin and Sean, thank you guys for all the hours you spent on Zoom and in the lab helping us out with this project, and also IFT for funding this project. So thank you guys.
Thank you.
Questions, right? Anyone has anything?
Great work, guys. There's so many pieces that had to come together. I've got a couple questions you can choose from, but I guess with the different ways to sense with the SLAM and the odometry, did you blend those together, or did those stay pretty separate?
Yeah, so with SLAM, we get a pose and we get the position of the vehicle and its location. And with the Imu, we were able to get kind of the linear acceleration and angular velocity. And then using the EXP node and using a common filter, we were able to get kind of estimates of like the states we wanted, specifically linear velocity and angular velocity, because we use that as references for controllers.
So there is some extended common filter.
Yeah, but the move base right now only uses the position output from SLAM, and we would like to use the odometry from the common filter. But the controller would already uses the common filter output.
And I guess with Ross, one more thing.
Yeah.
You seem to have the three separate Raspberry Pis. I can see there's a lot of integration.
Yeah.
And you described this as mostly a software project.
Yeah.
Like how did that like the version controller, there's some details that we're not seeing, and like how one person can work on one piece and the debugging involved kind of.
Yeah, are you asking kind of like the separation of?
Yeah, just like are there some more details with the I guess the software side of things, debugging things, or it would have been nice to see maybe more data or examples of like problem solving.
Yeah.
What's a good example of some?
Yeah, I mean, in terms of a lot of the issues we had was just implementation and configuring of the packages and stuff. The reason we like separated it was to kind of separate computation with heavy stuff, and preferably also to help with development. Also another like reason I thought of was like eventually if we only want to update kind of one subsystem, we can do that separately. But a lot of the issues wasn't really like conceptualized. It was just like kind of building or compiling stuff. And yeah, but
were there any issues though when you, did you develop those three things largely separately and then plug them together and?
Yeah, kind of.
Did that just kind of work, or was it a lot of?
So that's where we ran into like in the end we ran out of time trying to put them together. Because we ran when we ran SLAM that worked separately, and we ran manual control, we were able to kind of map everything out. And then running move base separately, once we plugged it in with kind of SLAM, it was able to output velocities. But then the last part, which was the controller, we had a controller kind of written up, but then trying to compile that and work it with the command velocities, that's when we ran into kind of compiling issues and we weren't able to finish that portion.
Everything was version separate.
Yeah, and like my guess would be with the controller, like it would work, but it worked poorly, and we would just have to tweak like parameters to make it work better. Any other questions?
Okay. Thank you guys.
Do we have to? No. you all on the sun or wait,
We don't have to.
huh? Do you have to?
I'm not.
You know, okay. All right. Good afternoon, everyone. We are Beehive, and our slogan is "Make Travel Smart." So first of all, let's talk a little bit about ride sharing. So in the past decade or so, ride sharing services have expanded tremendously, such that many people across the world have access to this convenient transportation outlets. So let's take Uber and Lyft, for example. Through the use of their respective apps, customers can request a ride in which drivers will get paid for each ride request that they fulfill. So in the end, that means everyone will be happy, right? Well, not exactly. We can't ignore the fact that there are certain problems plaguing these rideshare services like Uber and Lyft. So for example, since higher customer demand for rides is an incentive for drivers to accumulate higher pay, situations can arise in which there will be too few drivers in areas with low demand. So these very customers will have to wait an excruciating amount of time for their ride requests to be fulfilled. And this is even more prevalent in cases where surge pricing has taken effect, in which prices have skyrocketed tremendously to an attempt to reduce demand in these situations. So all of this make up the core of the central issue, which is the imbalance of vehicle availability and customer demand. So this leads us to our goals for this project, what we wish to accomplish. So in order to solve this vehicle demand imbalance, we need to be able to predict customer demand ahead of time. And if we're able to do this, we can then distribute our fully autonomous electric vehicles, which we will be employing the use of in our goals. We can distribute them in an efficient manner that is able to satisfy said customer demand. And accomplishing these two tasks paves the way for reduced wait times for customers, which is exactly what we desire. And furthermore, we wish to apply all of this to multiple different variations of customer demand in different cities and areas of operation, striving to generate a good amount of profit while also, once again, satisfying customer demand to the best of our abilities. And this animation, or the short animation here, gives a basic illustration of what we're trying to accomplish. So by controlling the movements of the vehicles along each route and the prices set along the routes, customer arrivals are being predicted at each of the different stations. And thus, the autonomous vehicles will then work in a efficient and centralized manner in order to accommodate for each arrival and to generate as much profit as we can.
So in the planning slide, we're gonna introduce about how our project is modeled. On this slide, we show how we divide the real magnetic map into 8 nodes, and by interconnecting them, we formed our map. And on this slide, we introduce some variables. So a typical process in our system would be like we have many nodes in the map, and there are many vehicles moving around to pick up the passengers. And note that the total amount of the vehicles is fixed. And we have customers showing up randomly at each node, but the expectation of the showing up rate will be affected by the price. Just like common sense, a higher price will reduce a lower demand and vice versa. So by that, we can affect the demand. And if a customer cannot be picked up on time, they will form a queue at the specific node there. So this figure shows a customer show up at node 1, and ideally, a vehicle will be moved to node 1 concurrently as the arrival of the passenger, and pick the passenger up, and the passenger pays the price and travel the passenger to node 3. So here we have reward costs and penalties. There are some performance evaluation indicators. The cost is what we have to spend to keep our system running.
For example, we have operating cost or mileage costs is what we have to pay for each vehicle travel every mile. And we also have penalties. Those are some relates to customer satisfactions, like waiting penalty. We added that to discourage our system from putting our passengers in waiting. And income is just the total amount we earn from the customer paying the price we set. And so our reward is defined by income minus cost and the penalties. So if we numerically maximize the reward, we should have optimized efficiency and profitability.
Okay, so in order to actually accomplish our goals that we set out to do, we employed the use of reinforcement learning. It's really easy to think about if you just think about how a baby learns how to walk. The next slide, please. So over time, we go from a state where a baby doesn't know how to walk, and to being able to we go from a baby not knowing how to walk to learning how to walk. And this is just a process of just trial and error and just refining its actions. Next slide, please. So we want to do the exact same for our project. So first, we have to be able to interact with the environment. That's this big old block right here in the middle. This is essentially our map, our Manhattan map, as well as everything else we need to know about our system, such as the distances between the nodes, how many nodes we have, et cetera, et cetera. So how we interact with our environment is we first start with our action here. And this is comprised of moving around our vehicles and what prices to set. And by taking that action, we directly modify our environment. And then we want to make an observation about that. So we pull out the vehicle distribution as well as the waiting queues of our environment. And we also make note of a reward. And this comes in handy later. So in general, we want to be able to take optimal actions. And we do so through a policy. We want to be able to train a policy to be optimal. And you can think of our policy as being a set of instructions that basically tell us what action we need to take. So for the sake of the argument, let's just assume that our policy is optimal already. All we need to do is take our observation, feed it into our policy, and out we get an optimal action. Next slide. So the hard part is actually getting and training an optimal policy. How do we do that? So as explained earlier, we have an action, we feed it into our environment, and we take out the observation and reward. Now, what the reward does is it basically is used to update and train our policy. So what the policy does is it takes our current observation and our reward, in a sense, it gets updated, and it gets used to influence and determine our next action. Now, over hundreds of thousands of iterations, eventually the policy will stop being updated, and at that point, we will say we have an optimal policy. Next slide. So for our purposes, it just turns out that using a neural network is beneficial to us. So it's the same concept. We take our observation and we feed it into our neural network, and out we get an action and a reward. The feed forward input of our, go back one slide. The feed forward input from our neural network is it's our policy. And our back propagation is a reward. We use this to basically train the neural network and our policy. Whenever we use a deep neural network, instead of reinforcement learning, we just call it deep reinforcement learning.
Okay, so when the system is getting larger, the number of variables in the observation space and in the action space is at the order of n squared, the number of nodes, square of the number of nodes. So when the number of nodes is becoming larger, then we will have a lot of variables at the input of network and at the output of network. And that means we need a very large network to train the system. And it could be very slow and resource consuming. And thus, our solution is to divide the network into multiple parts. For this part, we are going to use one network for every node. We are going to use one network to represent the to get the vehicle movement going out of this node and the price going out of this node. And the input of the network includes two parts. One is the common information that will be available for every network, that is the vehicle distribution globally and the total queue from each node. And that means the number of vehicles required for each node to clear each waiting queue. And they also include another part of the observation, that is the observation only meaningful for this node. That is the waiting queue going out of this node and waiting queue going into this node. Because we don't need information about the people waiting to go from node C to node D when we are deciding how many vehicles to move from node A to node B. So we can ignore that part of information. And by doing so, we are going to simplify our network by a lot and reducing the number of waits. So we can speed up the training. And this is the general data flow of the network. So we have the observation, we divide them into multiple chunks. One is the common observation that will be feeding to all the networks, and the others are the node observation that will be only meaningful for one of the networks. And then when getting the actions from each network, we combine them to form the actual global action. And this is the result. When we are using the dash lines are the result when we are using a simple, fully connected feed-forward network, and the solid lines are the case when we are using separated networks. The networks are of the same size, and you can see that when we are using a simple fully connected network, you will only achieve around average reward of 16. But when we are using multi-agent, we can reach around 27, and that is a great improvement. Actually, if we are going to use a very large network for fully connected, it can reach about the same level of average reward, but that will be too resource consuming and may take too much time to train.
Here's the animation of our A-node real data system. Our system processing the real data from the Manhattan, the real map, real distance, and the real demand price pair. Since it processes the real data, so there will be like thousands of vehicles and thousands of passengers which cannot be all shown in the screen. So we replace the car moving like previous video by indicating the number of vehicles and the passenger in each node. And our model is discrete time model, so the animation will run step by step. There are some data at the top of the screen. On the left-hand side, there is step number, profit of each step, and the total profit, which is the sum of the profit from each step. And on the right-hand side, there's gain, which will be gathering when the passenger come into the station. And the waiting penalty and the operating costs have been discussed in previous slides. The overflow penalty will happen when the queue of the station is too long to have more passengers. We have this penalty to have a better vehicle operation. And the node with the number means the mean node for passenger to have an order, and the small node in the past represent the car traveling. And you will see two different types of vehicle in the screen. The vehicle without person inside means the empty car, which is available to pick up passenger to their destination. And the vehicle with person inside means the traveling vehicle is not available. And you will see the small figure above the station represents the passenger, the queue of that station in the step. And you will see the data of the profit and total profit are on the increase, which is result. That's all combination of our hard work, and it is really close to the system to be used in the real world setting.
Yeah. So
yeah, thanks for your time.
Any questions?
I guess, so you're using the discrete time model as your real world
Yes.
for this. How are you setting like the time step for that? Was this based on maybe some publications? Like, is there a little more information why you chose a particular model and you tested it with different parameters? So I guess there's 8 nodes, there's a number size of each node and then at each time step.
Like this one.
Yeah, just, or even the last picture where you showed like the
They are
nodes.
the same one.
Yeah,
The way we discriminate it is that we set the like shortest distance as our unit of 1. So for example, the distance from 1 to 2.
but I guess what I think I get that. So there's longer distances
Yes.
and shorter, that would affect the time to get there.
Yes.
But if part of this problem, I guess, is how did you find a model for what traffic, like maybe in Manhattan, is it just random where things go? You're learning the best policy for this model. I'm just wondering about a little more details on how you choose that model.
We get the model for our advisor, Professor Moses Elizabeth, and his graduate student Berkeley, and they have publication about the system using other methods. And we are inheriting the model from them.
So yeah, simulating a real Manhattan
Yes.
data. And a system with only 8 nodes, is it possible you can find an optimal strategy because it's not that many nodes that you would compare?
Well, we can assume that all the vehicles in this region are in this node, and when there are like people in wanting travel from this node to this node, and we are just going to use like the most basic method that when the passenger shows up, the vehicle will move there and pick up and go. We will not do anything like we do here. This algorithm is mainly for vehicle redistribution when when in some time period most people want to go from here to here, and there will be a lot of vehicles staying here and not moving back. And we are going to use this algorithm to redistribute them so that we can have an optimal.
Right. I think maybe with the problem this simple, like deep reinforcement learning is one way to find a solution. And maybe for this case, there is a way to compare this, the deep reinforcement learning shows the reward is better or worse, but maybe not what the optimal solution is. Did you guys think at all about whether there's more than one way?
Yes.
A way to see how well you're doing.
We have another process, the static process. That means that every time we will move some vehicle to another point by a fixed amount, and it doesn't depend on anything, and the price will always be a constant. And but that policy has a very strict application requirement that it only works when we have enough vehicles to make sure that there will always be vehicles available. Otherwise, it will generate a negative reward. And when the number of when the constraints are looser, we will have the policy will tend to go into the static policy. But when we have strict constraints, like we have very high operating costs, or when we have like only small number of vehicles, then the policy will be very dynamic and it's much harder to change.
Yeah. I think some techniques like value relation might find an optimal solution.
Yeah.
But one last, I keep asking the questions, but I think everyone is excited by deep learning, right? So did you guys learn a lot from this project, and what was the most what's your takeaway from deep learning? How hard was it to get this to work? And what are your thoughts about that part of it?
I would say that there are just so many different moving parts that and it all just comes together to just work. It is a pretty amazing concept in my opinion. I definitely did learn a lot. I mean I was not like super familiar with like Python, but this was like completely based in Python. So yeah, I would say that I did learn a lot. I think we all did. Just working on it.
At the beginning of this project, we are actually trying to implement a value iteration, and that only works for like 2 nodes. When you increase to 3 nodes, the state space is too large to train. And that's why we switched to deep reinforcement.
Okay, through the value iteration, there's the 2 nodes, and then the other states are just the density state, I guess.
For validation, because we need everything to be discretized, including the price, and so we have like 5 different price, and that is a very bad model.
one little question from, I think the last slide where we're showing the simulation with 8 node.
Yep.
And you had this, maybe the second one there.
Yes.
If I recall, the overflow penalty is always 0. Can you remind me what the difference between overflow penalty and waiting penalty is?
Overflow penalty is just a penalty we use in the earlier stage of training that because we need a finite length of the waiting queue. When the waiting queue is filled, we cannot take any more passenger and we need a way to discourage that.
So, it's kind of like a waiting penalty, but you wait it way higher so that it goes away quickly.
Yes.
Okay.
So if you think about like, let's say we only want to have a maximum of 1,000 customers in a queue, we say, okay, stop taking in customers. If you were to take in one past that overflow, that maximum 1,000, we heavily penalize it to say, okay, don't do that in the future. And that's just to prevent like us from getting like really long like waiting periods and lines for everyone that wants to be serviced.
Okay. Rest of time, let's move on. Thank you.
They should be. All right, hello everyone. We are Arthroscopic Unlimited Vision, and our project is focused on enhanced instrument imaging system for arthroscopic surgery. The team members are me, Ria, Caitlin, Kelly, and 2 of our members will be talking through Zoom. So they're Kelly, Ethan, and Sean. So arthroscopy is a minimally invasive procedure that it used to diagnose and treat joint issues. On the surgeon's end, arthros kind of identified some problems that we were going to address. One of which is keeping track of an instrument's location, the instrument being the medical device with respect to the endoscope. This is important because sometimes the medical device is obstructed by communication. And so since this project was initially for a multidisciplinary team, much of the specifications were designed towards having a full multidisciplinary team, some of which is to create a product that allows surgeons to freely articulate the instrument in space and to accommodate all degrees of freedom. Now, over the full fall quarter, we had done some research on tracking methodologies. We had also talked to an orthopedic surgeon, and we did a lot of research on current products in the market. So here we decided not to have any mechanical components or additional and potentially intrusive devices such as like electromagnetic sensors on the medical device or using ultrasound for tracking. And we wanted to strip the problem and make it as simple as possible. So the first design that we had considered was having a overhead sensor and tracking the endoscope and the medical device using markers. This is really similar to motion capture technology in entertainment. And then the second design that we decided to eventually go with is using the endoscope images and a pattern. This pattern would have some sort of encoding on it that would help us identify where the location is on the images. Now, given that we had worked completely from scratch, we decided to use Python and MATLAB to test and develop our algorithms. We also decided not to use any new tools, so we are completely using Arthroscopic's UHD4 camera controller unit to get the input images. And we are also using existing medical we are using is called the Debug sequence, which we will later discuss. And so to begin, we take the images from the camera controller unit and in an ideal setup. So we changed the scope of project to an ideal case. So we changed the scope of project to an ideal case with several constraints. So we made changes to our setup accordingly, and this is the drawing of the setup. The first constraint is the endoscopic camera is positioned perpendicular to the instrument and the obstruction. And the second constraint is the instrument is allowed to move in a lateral field of rotation. And the third constraint is the instrument can be placed at various distances from the camera. And lastly, a polarized sheet is placed in front of the camera to avoid reflections due to direct light from the endoscopic camera. So by using this setup, we're not considering the rotation out of plane. The next two pictures show you what our actual setup looks like. We have chosen a round edge obstruction because first we want to mimic tissues inside the body as obstructions, and secondly, we don't want any other straight edges in our input image besides the shaft of the instrument, because they might get picked up by the straight edge detection and interfere with our later calculations. So in the middle picture, in the front and center is the endoscopic camera sitting on top of the stand and pointing at the obstruction and the instrument. And the camera view from this endoscopic camera is displayed on the monitor in the back. The next picture was taken from the other side of the setup, the same setup, where you can see the instrument is placed inside the stand and sitting on top of the slider so that it can be placed at various distances from the camera. And also there is a rotation mechanism inside so that the instrument can be rotated to any position on the XY plane parallel to the endoscope face. So this is the setup we've been using to get our input images to our algorithm pipeline. So this is our algorithm pipeline. First, the input images going to the pre-processing to correct the fisheye distortion from the lenses. But since we've been testing our algorithms without this filter and getting expected results, we're not applying this distortion filter right now. So instead, the input images first go into the edge detection algorithm, which performs the edge detection and isolate area of interest, which is the instrument, and then crop it out and rotate it to a horizontal position. And then this output is given to the next part, which is the pattern recognition algorithm that uses the Bruin sequence to find out where we are along the shaft of the instrument. And then this information is given to the last part of our pipeline, which finally puts an endpoint marker on the image indicating where the tip is.
So the first part of our algorithm is the straight edge detection, where we begin with importing many libraries, primarily OpenCV, so we can use its many key functions. We then switch to grayscale to improve the contrast in our images and efficiency in our algorithm. Then using hue-line functions with calculated thresholds on the parameters on each unique frame will help us find the ideal lines that we want. To further this, we set those list of lines through filters to get the exact lines we want, which are the edges of the surgical instrument. So you can see this on the right side where there's a before and after comparison where the bright green lines signify our final output in this step. So moving on to the next part of our algorithm is copying our tool. So we do this by using the coordinates of the two lines previously mentioned to make calculations. This includes finding the height, width, and angle of the new line from our outputted reference point. And with these calculations, we are then able to fully separate our tool at an upright angle to move into the next part of the algorithm.
Okay, so before we continue down the pipeline, I wanted to explain the idea behind de Bruin sequences. So essentially a de Bruin sequence is a binary sequence where a certain number of bits are always unique, and that same pattern can't be found in any other segment of the sequence. For our case, we decided to use a 32-bit sequence, and for that, we would need to see at least 5 bits out of the entire sequence, and our algorithm would work. So we decided to use this concept because due to simplicity and visibility for image processing. continue down the pipeline. We take in the cropped image, which is used to extract the reference and De Bruijn bits. The reference bits are used to understand the width of each bit so that the De Bruijn sequence can be understood and downsampled properly. Finally, we just truncate down so that because we only need to see 5 bits, and we're able to extract information such as knowing how far we are along the instrument and how far we are from the tip.
Okay, so we're in the last part of the pipeline of the algorithm, where we are trying to estimate the endpoint of the tip. So we go through 3 steps in order to do this. To begin with, we're taking in 3 data points from previous parts of the algorithm. We're taking in end coordinates of the instrument from our straight edge detection, which will give us a starting point of where to shift from. We're also taking in a pixel to distance ratio, which is essentially the number of pixels per millimeter, which helps us convert back and forth between images and real-time distances. And then we are also taking in the section number of the first visible bit, which is essentially the number of the bit that we see on the image. And we take in all these 3 data points and we use them to calculate the number of pixels we need to shift, starting from what we see here, and then we move on and calculate or we mark the final point. And this is a close-up of the image that you just saw. The X marks where the tip of the instrument would be from all our calculations.
All of these neon bright light source, and an image management system, and a fiber optic video, all in one tablet control device. So this is a tablet that wants to take images and videos for all of our test cases. And then we have the screen that takes in and you can also we consider the cases where the instrument is allowed to move over one and move at different distances away from the camera. For a setup, we are using a custom prototype where instead of creating a surgical instrument, we printed the same pattern on the end.
Okay, so the first part of our algorithm takes this initial frame and doing some calculations of the thresholds and parameters and some filtering. We're able to find the exact concept we want, shown right here, the blanking line. And you can do a side-by-side comparison to seeing when it's being cropped out after you're using those 3 lines to calculate the width, height, and the angle showing up. And then we know the next output for each pattern. So from each code, we get the image here and find the reference and the reference, and from there find the problem failure. In this case, on section 2.
Okay, so in the final part, we're inputting the section number of the first visible bit we see and the coordinates at the ends of the instrument from the previous 2 segments of code. We're also using pixel to distance ratio, which is the number of pixels per millimeter. And we use these inputs to determine how many pixels to shift along the instrument for reaching the tip. So this is our output, and the center of the X is the estimated location. We also calculated accuracy, so we are 1.24 millimeters away from the actual tip.
So for our final thoughts and conclusions, we first had a very unique project where the problem given to us was very open-ended and could be solved through various methods. This included going through end-to-end development, meaning we had to research and brainstorm many different ideas, tailor our specifications, and make significant progress on our solution. The next steps we plan to accomplish were first converting our algorithm to be able to fully take a recorded video, and after it has a high accuracy and efficiency rate, we will be able to move on to using live feed inputs. And for moving past ideal cases, we want our tool to be able to move at all degrees of freedom, so we would not be restricting the z-axis in this case. And for the pattern design, we want to shift our De Bruijn sequence from our pen prototype to an actual searchable tool using laser markings. And lastly, instead of having an endpoint estimation for the tip of the tool, we would like to visually reconstruct hidden parts of the tool over the obstruction.
Thank you. Any questions?
Were you able to change the angle of the instrument that you're trying to see, or did it need to be pretty much horizontal?
Yeah, so for our ideal case, we are able to move the instrument in a XY plane. So we are able to change our angle for images. Yeah.
Great question. Did you see what the accuracy was? Like if you took another picture with the obstacle moved away?
Yeah, so the way we calculated our accuracy is before implementing our algorithm, we decided to mark over the obstruction where exactly the tip of the instrument would be. And then we implemented the algorithm over that image, and we calculated the pixel distance between the 2 points and then converted that to real distance.
What was the accuracy approximately?
So I wouldn't be able to give you a number in percentage, but for this particular example, it was 1.24 millimeters away from the actual tip.
And then one last thing. Did you guys think about parallax at all? Sometimes when you look at a camera picture, it's like in one part of the picture, that scaling is going to be different than somewhere else. Was that important, or did you think about it?
Fiona?
Thought about it, most of it was with regards to at least the distortion. But when we had implemented some of the distortion correction as opposed to having it without the distortion, it came up pretty similar.
Oh, great. So you did look at that. You did a filtering to kind of look at this point. Excellent. Yeah. Nice work.
Great, thank you.
This one drop over there. The last one over there. All right, should get started. Hey guys, so we're the ASML Capstone group, and I'm Lawrence. Austin.
I'm Dylan.
All right, so let's quickly introduce our sponsor. Our sponsor is ASML. They work in the semiconductor fabrication equipment industry, and they do something really unique with regards to lithography. Okay, yeah. And then they do something called UV lithography, or extreme ultraviolet lithography. So as a bit of a background, what lithography is, it's a process of improving the chips that go into almost everything you have nowadays. Your CPU in your phone, SoC, GPU is in part produced by lithography. So the process of lithography is you land a mask on top of a wafer that has your features defined upon the mask, and the light goes down to the mask and exposes the exposed part of the mask, and then that helps define your features later on in the process. And that exposed flows photoresist, which is something you layer on top of your wafer, which is exposed by the mask, helps form your features such as your transistors in your device itself. So what is UV lithography? So as your devices get smaller and smaller, you need to make smaller features. And as you know, it's all the smart tactics of packing more transistors into a CPU or GPU itself.
So we work at a really small wavelength of light, 13.5 nanometers. Perspective, the last generation was around 130 nanometers. And that fine feature selection is controlled by a lithography light source. So how is UV lithography light created? So how it's created is that we have a thin plasma droplet that's being dropped at 50 kilohertz, and it's hit by two lasers. The first laser flattens the droplet down. You can see this droplets being flattened down below. And the second carbon dioxide laser vaporizes the droplet to produce the infrared light that you see emanating from our source. And the reason for this is that we have very scalable power and very fine feature control, which is why we have this vaporization process. So what's the problem that we're dealing with our project? So sometimes after you hit it with the first pulse where you flatten the droplet itself, that shape is often irregular and not consistent, and that can lead to poor feature control, and even really in bad cases, it can explode and damage the machine, which will reduce your production yield and have machine repair times. So our project uses computer vision, optimization, machine learning, deep learning, other techniques to help predict the plasma performance. So how do we do this? So here's a droplet generator subsystem. So we're focused on two things called droplet formation cameras, or DFCs for short. So there's two cameras looking at the droplet as it's being shot down orthogonally. You have two cameras, and then we're examining the droplet after it's being flattened. So as you can see in the two pictures to the right, we have droplet formation camera 1 and 2, and that's how we're observing the droplets as they're being hit by the lasers. So here's just a bit of summary of that. We use those two images to help reconstruct the droplet in a three-dimensional space. And we use that to help predict if we predict good plasma quality or not. And as I said before, consistent droplet formation gives you consistent plasma, which is consistent light source, which gives you good chips. So what's our primary goals of our project? So ASML's the current code base have we improved by improving complexity and all those other things you see there. And we also have a new techniques of analyzing the metrics that we outputted with either image and image quality, see if this image is even okay to predict plasma quality, and also taking those features from 3D reconstruction to see if we get good plasma or not. And here's just an overview of our two systems. This is the current base that we have to take in the two input images, and we come up with the output 3D reconstruction of the droplet itself. As you can see, they're orthogonal, and those two planes is how we construct the image itself. And here we have a bit of a quick pipeline we'll go over later about our machine learning and deep learning techniques. And we can get started over our subsystems.
So in order to analyze the picture more efficiently, we need to first extract the plasma from the background and remove any noise, so we can then analyze the plasma and extract its parameters, which is going to then be passed on the model, 3D model reconstruction. So the first thing we do is we perform a background subtraction technique where we take a background image and subtract it from the DFC image to identify a region of interest, in this case the droplet, within the image frame. And then we apply a bilateral filter, which also correlates pixel values within the image on the spatial and range scales. So it preserves edges while also smoothing pixel values to help with thresholding. And then we perform histogram analysis to determine a threshold and binarize the image to remove the background, the noise in the background, and extract the plasma within the frame. So once we've pre-processed the image, we can then perform analyze the spatial characteristics of the droplet through an ellipse fitting method, and then extract the parameters, which is then going to be passed down into the 3D model reconstruction, so we can classify the droplet. So the problem with the old algorithm is that it ran on custom-made programs that tend to be inefficient and not standardized. So our solution to this was to use standardized MATLAB algorithms and implement this within the code to improve and standardize the algorithm using these standard MATLAB libraries. So in measuring performance, we use the two foci definition of ellipse, which is an alternative definition of ellipse, which states that an ellipse is the set of all points whose sum distance from the two foci is a fixed constant d. So then we can get the standard deviation between the border pixel list of the plasma within the frame and analyze this. And so a perfect fitting ellipse would have an ideal variation of 0. So after analyzing the old algorithm and the new algorithm, we got that the new algorithm was 11.8% closer to this ideal variation of 0 when tested on 34 different images. And we ran a two-tailed t-test to make sure that these two were statistically significantly different. And we got that they were, so we can conclude that the new algorithm is significantly better than the old one after implementing these libraries.
Okay, so this is the 3D model reconstruction process.
This is filter and image pre-process and initialization, optimization, and simulate image and error calculation. If the error is larger than threshold, we will go back to do another optimization. If the error is acceptable, we will go to the generated 3D model. So our 3D model will calculate the feature matrix, major and minor axis, orientation, and curvature. And we use the FMEANC in MATLAB as our optimization function, which find the local minimum using the transfer region algorithm. So the ASML algorithm optimizes all 4 features. It costs about 100 seconds for each image, but we got improvement. We determine the effective feature is curvature, so we apply our FMEANC only on curvature, and it costs 22.6 seconds for each image. We got 70% reduction. Yeah, and this is the whole optimization process. The goal is to find the best simulated image result. We do the optimization first and find the simulated image and find the error rate by calculating the mean square difference between the raw and the simulated images and generate 3D model if the error is acceptable. So in the right side is the simulated image, DFC1, simulated DFC1, DFC2, and simulated DFC2. And the lower one is the 3D model.
Hi, we want to cut down the optimization runtime and to provide better process metrics for data classification for deep learning. We are also going to try to find a new model. Like here, we use the fitting for the feature extraction and the 3D cross-stacking to build the 3D model. Here we have 5 steps and to test the code performance. Here, for the X fitting, use the intersection divided by the unit to see the area overlap for both DFC1 and DFC2 images. For DFC1, we got a 92.1 on average of total 275 tests, and for DFC2, we got 94.28% accuracy, which is better than the EDIF for 88 and 89 accuracy before. And also for the cross-stacking method, we can see the left-hand side is the side field for the 3 more board, and after output, we can see this is the DFC1 and DFC2 image after crop and resizing. Here we imply the negative DFC2 angle and negative DFC1 angle from the field set of 90 and the minus 90. And also for the side field area, we also apply the overlapping test, and we can see for DFC1 image we got 89.72%, and for DFT we got 95.13% accuracy. And for the improvement, we can see that original code base just provide less accuracy and less flexible since it only has the major minor axis and orientation. For the new code base, we build on the ad fitting process, and we have the major length express the distance between the express and the middle x position, and the express as 3/4 of the x position, for both up and down side of the x, since I'm not implementing a symmetric on both sides. And for the old one, just represents for the perfect ellipse shape, but for the new one, we can compatible with irregular shape like oval and paraform and otherwise. And for the runtime, it takes about more than 3 seconds with optimization, but for the new code, it takes about just 0.5 seconds without optimization, and it still achieves a high accuracy that we can see.
Yeah, so after we get these features out of our reconstruction, we can actually plug them into a machine learning model. And then we're going to go over actually how the features are ranked after a model. So we use something called RFE, which is called recursive feature elimination, to help determine which features were most pertinent. And we help that to feedback to our optimization and our reconstruction, both machine learning models, to see which features were actually pertinent to entire process to optimize it. As you saw before, we eliminated many of the features except the curvature. So based on that, we just found some useful and not useful metrics to actually determine plasma quality. And we'll go over our models next. So here's the useful metrics and not as useful metrics.
So one of our goals for our pipeline is the machine learning for plasma classification. Ideally, we want to be able to create a model that can correctly identify good plasma, but more importantly, correctly identify bad plasma. As if bad plasma gets through, it can cause, as mentioned before, expensive damages to ASML and it leads to a lot of setbacks. On the next slide, we'll talk about the method we use for this classification.
So we came up with actually a pretty novel technique called ADA boosting, which is a method that combines a ton of small classifiers together to find some cross-validated consensus to be able to classify our plasma qualities. So we combine this with something called oversampling, which does have some downfalls, but we managed to get a model that actually perfectly classifies plasma qualities for bad plasma all the time. So it has no false negative rates for classifying bad plasma. So as you can see in our confusion matrix here, that we're classifying bad plasma 100% of the time while sacrificing around maybe 0.5% of the good plasma to be not used. So ASML, their machine itself, has a failsafe for not, and as you remember before, the pre-post and main post, they have a failsafe for not vaporizing the droplets when they detect bad plasma. So that's something that we implemented. And our model beat the previous model by around 25%, and it beats non-oversampling technique, beat a non-oversample technique by around 5%.
So in an application of deep learning within the project, we got a data set of approximately 34,000 different images, of which 4,000 were labeled as not okay. And we wanted to try and classify the the droplets from the raw image data alone. So using this, we trained two deep learning models, a custom-made CNN and AlexNet through transfer learning. And trained on this data set, the custom-made model, which is of low complexity, comprised of 7 convolutional layers and 1 fully connected layer at the end, achieved pretty promising results with a training accuracy of 98.19% and a validation accuracy of 96.1%, with an average runtime of 2 milliseconds tested over 4,000 different images. And then the foundation model, AlexNet, is of middling complexity, comprised of 8 layers in total, with 5 convolutional layers and 3 fully connected layers at the end. And this actually achieved on even more promising results trained on the same data set, with a training accuracy of 99.84% and a validation accuracy of 99.6%. However, due to the increased complexity, the runtime was 40 milliseconds when tested over the same 4,000 different images.
Yeah, so we're going to go over a short demo. I think it was primarily software based, so it's primarily going to be code. So I'll just narrate it a bit. Yeah, so first we have our ellipse fitting that we demonstrated. So we're just going to show the code in MATLAB for it. Most of our code is done in MATLAB, except for deep learning and machine learning, which is done in both MATLAB and Python. So here's an example of 2 droplets that produce good plasma, and one droplet produced good plasma, one droplet produced bad plasma. I'm just showing how we threshold it and borderize it. And next we show the reconstruction we get from that. And this is a bit sped up because we do have an optimization technique that does take kind of long when you do implement it. So this is sped up. So this is just 2 reconstructions of a good image, plasma that creates good plasma and bad plasma. So here's our simple boosting method that predicts good plasma or not. So it actually predicted our 2 sample pictures that we have below. So predicted that good plasma is not bad and bad plasma is bad. And here's our GUI example where we got a user interface of just doing the whole thing at once. And yeah, we have the custom model that Austin said was slower, and then the new transfer learn AlexNet model as well. Yeah. It won't. Let me get out here. Yeah. Okay. Okay. So our key takeaways, as we mentioned for our first project objective, we want to improve on the original code base. So we managed to improve the ellipse fit, as previously said, by around 12%, and we also increased the optimization speed with one reconstruction method by 70%, and we managed to reduce the reconstruction speed with the alternative 3 fitting method by from around 100 seconds down to half a second, which is a pretty substantial improvement. And from the machine learning and classification technique, we found out that our neural network actually classifies image quality pretty fast, around 2 milliseconds. And our machine learning method runs in almost negligible time, which is really important. As I mentioned before, our droplets are being generated at 50 kilohertz. We want to sample as many droplets as possible. So that was why runtime was a pretty big factor within our entire project itself. And then therefore we can say that we completed our project objectives, and we also managed to create goods models themselves. I think that's it. Yeah. All right. Thank you. Any questions?
Backing up to the original application of this, I think you said that there were drops generated at 50 kilohertz.
Yeah, the plasma droplets are being dropped at 50 kilohertz, but our camera captures at a lot slower rate, around 20 FPS.
Okay.
So that's, I guess, a discrepancy within that itself.
So there's not a need to evaluate every single drop.
Yeah, they just want to maximize. Yeah, there's not really any time to get as many drops as possible. We just want to maximize the number of droplets we can process with our runtime.
Okay. Just so I understand, like exactly the pictures are always from one particular angle, not.
Yeah, they're always.
3D reconstruction, but it's based on.
There are like 2 cameras, like one is this
Okay.
and one is.
It is, okay, so there's, yeah, sometimes when you have like the.
Yeah, the 2 cameras are always, yeah.
For the 3D processing, just like one camera and it, like on the platform and then rotate and squeeze it to the same frame, and then you can drag it along.
So the camera is, they're precise enough here to instantaneous.
Yeah, we treat like the camera are like the same like distance from the droplet, so like the relative size is like so we can say, yeah.
Very cool stuff. And then finally, I assume that the guys at Cymer, ASML, are trying to understand how to improve this whole droplet process. But these are always pictures at a particular height, I guess.
Yeah, the cameras are stationary, and I think one of the things they want is to be able to. One of the main things they want is which features are most pertinent to plasma quality, so they explore actual physics behind it.
How do they tell something's gone wrong, and then how do they understand the process of making droplets?
Yeah.
Yeah, so I was wondering if, but they don't have sequential, because it'd be interesting to get sequential pictures to understand the droplet formation.
Yeah, the thing is, it happens so fast that the camera capture rate doesn't really capture the entire process. I think in one of the diagrams earlier, it's just a 3D or a modeling rendition of how the droplets are flattened. I think right here. Yeah, so essentially the final droplet pancake varies. That's what they want to look into when producing actual plasma.
Yeah, that's great work. Just so that we're all visualizing what's happening, like going left to right, like where's the direction of gravity for this?
Yeah, so it's going left to right, but the gravity is downwards. The droplets are going downwards, and then they're being flattened by the carbon dioxide laser right there, or they're being flattened by carbon dioxide the laser, and then it's vaporized into the infrared light.
Yeah, the gravity is down, the drop.
Yeah.
But gravity is blasting from the side.
Yeah.
Yeah. It's hard to imagine like what the stone trees are being driven like stretched by gravity.
Right.
Yeah. That's kind of cool. That's about it. I mean, how much do you guys know about AlexNet or any of that coming in, and what was the most I don't know. What got you excited about the project, and what was the highlight, I guess?
Yeah, so I was actually, I took the machine learning / deep learning series here, so I had a lot of experience with that, and it helped applying it to the project. would say the hardest thing was applying deep learning specific to the plasmametrics, or trying to, because it's information poor resource compared to the images where you have about 50,000 pixel values compared to the 30 plasmametrics. And then also the data set is highly imbalanced. So I treat it as an anomaly problem, trying to classify it that way through deep learning, but it was more of a machine learning thing, machine learning solution in the end.
Really nice. I appreciate all the data.
Hello everyone. We are PLC. Our slogan is Automation at Ease. And my name is Ben. My teammates are Sebastian, Jinghua, and Long, and Harry, who will be joining on Zoom. So this will be the overview of our presentation. So first, we're going to talk about the background of the PLC, and then the problem that we are facing, and the goal of our project, and as well as the solution we come up with, and the result we obtain from them. And at the end, we will talk about the cost of our project. So background. So what is a PLC? So a PLC, or programmable logic controller, is a special computer device used for industrial control system. It most commonly has I/O module that consists of analog and digital input/output, including relays. It also have a communication interface or protocol, such as one wire UART or I2C port, or like Modbus. So we're gonna moving on to the problems.
Okay, so along the way of developing a PLC, and there will be some problems along the way that we need to solve. And one of them is the EMI, or the electromagnetic interference, or EMI. Now, those could come from a lot of sources, but since we're planning to use our PLC in an industrial setting, some of the common sources are high current cables, motor, and other industrial machines and equipment in the factory. With all of those interference happening in a enclosed area, the interference could be extremely unpredictable, and with those interference presenting in the environment, we could potentially get some problem with the signals. There's also some source that is internal, caused by shot noise, thermal noise, or 1/X noise that we also consider, but after extended research, we found those are less influential compared to the external one. So we will be focusing on the EMI generated mainly by the motor and other machine equipment that would typically range between 20 kilohertz to 100 kilohertz in those environments. Another problem that a lot of PLC does not have right now is a human-machine interface, or HMI. Those interfaces could allow the operator to monitor, control, and debug or analyzing the process data easily. With the help of HMI, it makes possible for people with less skill sets to quickly analyze the problem and come up with a solution to maximize the production time for the industrial system. And we will be moved on to the project.
So combining with the background information and the purpose with PLCs. The purpose for this project is to create a low-cost noise reduction PLC and simultaneously construct an automation systems. To reach these goals, the key components to be utilized for the PLC control and noise reductions. We use the Raspberry Pi 4 and the connection with the UniPi 1.5 extension port to play the PLC function. And we use the IO periodic cage for the EMF protection. And there is a low pass filters, and we use a touch screen display to play for the HMI function. For the key components utilized for the automation systems, after 1 year's Raspberry Pi design use the ultrasonic sensors, color sensors, linear actuators, and conveyor belts.
So on our PLC, we'll be using a Raspberry Pi as our processing unit. However, Raspberry Pi alone is insufficient just for the serial process because there is a lack of protections, high power output, and relays. And it also does not have the ability to have analog output. Thus, we have added an extension board to solve the problem. So the extension board will have 8 relays and the 12 digital input, 2 analog output, and a lot more that could support that very large variation of process. And for the HMI, we will be using a touch screen that is directly connected to the Raspberry Pi. And we will be programming a user interface that allows us to display all the information that we needed for specific systems. And for the noise reduction, we implemented 2 methods for it. The first one is a Vertex page that could both physically and electromagnetically protect the main processor that, and we ran some tests for it, and it's able to protect frequency range in the interest 20 kilohertz to 100 kilohertz. We also added active noise filter to counter any incoming analog or digital signals. So this is the Sally active filter. It is capable of filtering noise in the desired range from external source such as sensor, which we would expect them to be put away from the main system and have signal traveling through the cables. We will move to the testing results.
I'm not able to see the slides right now. Do you want me to just go here without seeing them? Can you guys hear me?
Yeah.
Oh, there you go. Okay, so moving on to HMI. Our human machine interface will be displayed on the touchscreen monitor, and they'll be divided into different pages. By clicking on the button on the top left corner, you'll be able to switch between these pages. And the first page will be the main page where it shows you the combination of status, control, and graphic page. And the following pages will show you this information independently, which next slide will be the status page. It will display the status of the color detected by the color sensor, whether the linear actuator is on or off, and the status of the conveyor belt. Moving on to the graphic page, which it will show you the current operation of the color sorting system that we'll implement using our PLC, and it will be demonstrated in our demo video. And lastly, we'll have the debug page, which is not included on the main page, but it will show the status of digital input, analog input and output relays for troubleshooting purposes.
Moving on to results for noise reduction. So first, we're covering the PCB filter. To the left, you see the schematic that we designed on Eagle. To the right, you see the filter performance. This filter was designed to be good up to around 500 hertz. Basically, the only caveat to our design is signal degradation, but that's really not a problem since the second stage of our filter is it has a gain stage with a potentiometer. It has a relatively compact size of 1.1 by 3.2 inches. It's pretty low cost, $8 per unit, and it's linearly cheaper with more boards. So here's an image of the performance. In the top, you see a clean 60 hertz sine wave at the input of the PCB. In the bottom, you see the same sine wave with a noise signal also at the input. And these are both the output waveforms. So basically, the noise was reduced, but the signal was also degraded. So moving on to the Faraday cage. To the left, you see the Faraday cage. To the right is the performance. We performed a sniff and spray test at both 350 and 425 megahertz. We basically sent 10 dBm of RF power, and the minimum signal isolation we saw was 9.96 dB. The reason why we didn't spray more RF power was because we didn't know if we could do this legally per FCC regulations. We weren't able to get a waveguide that allowed us to test our system from the frequency range of interest, but signal performance should be much better at lower frequencies regardless. The only caveat to implementing this is the weight. It's about 8.5 pounds. The cost is about $44 per unit, and it's much cheaper with more cages.
So for our demo, we'll be constructing a color sorting system using our PLC, and these are the core components for our system. And let's just jump right straight into the demo video. Now explaining how it works. And so this demo video, our system is set to differentiate 3 different colors, which are going to be red, white, and black. And the conveyor belt will deliver the object to the ultrasonic and color sensor, and they'll be pushed off from the conveyor belt by the corresponding linear actuator depending on the color reading. So as you can see, the graphic widget on the side of the screen will show you the movement of the object and the operation of the linear actuators. And then on the HMI, there's also a count function which will update the presence of the object that is being detected along with the correct color reading. Then it goes black, which will activate the 3rd linear actuator, and it's all showing on the screen. And yep, that's pretty much it. Move on.
So move to the project class and list the tables to list all the items for this project, including the sale tax and the shipping fees. The total cost for this project is $1,800. Do you have any questions?
Yeah, I don't know. Did you have other, like with the sorting, other answers also? So I noticed like that linear actuator is like twisting, as it's pushing objects. But how is that? Is it because there's a screw actually turning inside? Or like I guess when you push it, it doesn't just extend, it's actually turning as it extends. Is that just the way the actuator works?
Yeah, I think that's just how the way actuator works. We did not actually make those actuators. Here we produced them online just to demonstrate that our system works. And for the system, we just create them to demonstrate that our PLC will be functional as intended. So as we are able to, I think we are able to implement a kind of system that uses less than 8 delay. And then we will have to change the software on how it functions. But I think it is capable of supporting a lot of different systems.
On the input filters where you have the syn key filters, was that you said it was a 500 hertz with that filter? Is that how did you choose 500 hertz?
Most analog sensors have transmit data at around that frequency range, so that's what we went with for our design.
Okay.
Yeah, so I mean, I guess we've seen, did you cover both the software, the GUI for the MATLAB, and then we're also designing the circuits in it. Everybody kind of take a different role or not in integrating it all.
But what was the GUI written in anyway? Node-RED. What was that?
So we write it in Node-RED because we did some research and find that one of the most common logic programming language that's going to be used in the program, which is why we choose that program and also create.
Thanks, guys.
Thank you.
Does this work? Are you able to hear me? Yeah, we can hear you. Just tell me when we should start. Are we ready?
Yeah,
Are we
go ahead.
All right.
You want to talk a little bit louder though.
Okay. Hi, everyone. I know you can't see me, but my name is Justin. And for the past 9 months, I've had the pleasure of working with William, Sean, Alina, and Ethan on our senior design project, MIMO. MIMO is focused on laying the groundwork for future radar designers by developing a wirelessly synchronized millimeter wave distributed MIMO radar network. And so I know that's a lot, but we'll break it down in this presentation. But before we do, let's take a look at the motivation behind this project. So in the past couple of years, a lot of attention has been centered around autonomous vehicles and getting to level 5 full automation. But currently, modern systems today are only at level 2 or level 3 autonomy, meaning your car might have a more advanced cruise control system or maybe an automated parking system. But either way, the driver needs to be attentive 100% of the time. And so one of the issues that is preventing us from getting to level 5 full automation is the issue of sensor interference. And this is especially prevalent in dense urban environments, as we could see on the right-hand image. The orange car has a very limited field of view due to obstructions in its line of sight. And these obstructions can be coming from other vehicles, buildings, pedestrians, motorcyclists, etc. And so this is a real issue, because what if a child runs down the middle of the street, or we can't see a bicyclist in our blind spot when we're trying to make a turn? our car might not have enough time to react. And so this is where we come in. So how is MIMO attacking this problem? Well, our system consists of 2 independent radar nodes, each consisting of a FMCW transceiver, which sends and receives our chirp signal. That is then connected to a data capture and streaming board that then allows us to download the digital data to our computers for post-processing. And so where we differ from modern solutions and other research groups is that we actually implement a coarse wireless synchronization between the 2 radars that allows us to share the data between both radars and provide each radar a larger view of its surroundings despite line of sight obstructions. And so we could see on the right our functional block diagram. We first established the synchronization link between the 2 radars, send the same chirp parameters to both radars. Those radars will then image the scene of interest, undergo its own signal processing chain before being sent to our data fusion GUI, where we'll then verify our results. All right, cool. So we're sharing data between 2 nodes. Might seem simple, but the key is we're doing this via a wireless synchronization, and that's really the magic here. And so for us, our goal might just to be able to see a person moving behind a car, which we'll later show, but the application for this is really exciting and should get you excited too, because where we see the future going is that every car has its own radar, and they're all synchronized together wirelessly, and they're all sharing their data together in real time. We could even have radars on top of traffic lights, street signs, light posts, all sharing their data together in real time via a wireless synchronization link. And so essentially, this will provide every car a massive bird's eye view of their surroundings despite any possible line of sight obstruction. This will even allow cars to see corners, which again, we'll get to. But this is the level of safety that we want to push society towards, and it all starts with wireless synchronization. But before we showcase our results, we need to understand how we get there. So I'll let Sean talk about our chirp parameters.
So now I'm going to talk about some of the parameters that we have control over so we can set up the ideal signal depending on what type of scenario we're in. So as mentioned earlier, we are dealing with transmitting an FMCW signal, which stands for frequency modulated continuous wave. And that basically means that the frequency of our signal is going to change across time. So if we look at the top graph, we see that we start at a start frequency of around 77 gigahertz, and then the frequency linearly increases to 81 gigahertz, and this constitutes 1 chirp signal. So something that we want to take into consider is the difference between the start and the stop frequency, as that determines the maximum distance that our radar board can detect. And then we also want to consider how fast we arrive from the start frequency to the stop frequency, which is determined by the slope, and that'll help us determine the distance resolution or how small of a distance the radar board will be able to detect when we're talking about 2 objects that are close together. And then some other parameters we want to consider are the idle time and the ADC start time, which basically delineates the difference between the end of our most recent chirp signal and the start of our next chirp. And now once we've determined how our chirp signal is going to look, we're going to want to send n amount of those chirps for one particular frame, as this will help us resolve information related to velocity. And then these chirp signals we'll have n chirp signals be transmitted for one frame, and then this is going to repeat for however many frames of data we want to send out. And then these chirps can be sent simultaneously by all transmitter antennas in a binary phase modulation or BPM format, or we can choose to have each transmitter antenna transmit these separately across time in a time division multiplexing or TDM format. So if we go to the next slide, once we have captured our data from Millimeter Studio, we have an interface that we can work with to figure out basic rudimentary information about distance and velocity. But this is not enough to work with if we want to be able to achieve our goal of data fusion. So after we work with Millimeter Studios, we export this as a binary data file, and we take this over to MATLAB, where it's converted into a more convenient format that we like to call a cube data file. This basically makes it easier to separate the data across the chirps, the antennas, and however many ADC samples and frames of data we've been working with. So now once we've done that, we can perform a range FFT and a Doppler FFT to resolve information related to range and velocity. And then we can perform BPM decoding if necessary, depending on the type of signal that was sent. And then once we've done this, we can perform static clutter removal, which basically takes a static scene comparison and removes that from the range Doppler maps that we've been looking at to remove any potential noise points. And then an OSC-FAR detection algorithm, which stands for Ordered Statistic Constant False Align Rate Detection, which can basically detect determine whether or not we have legitimate objects that we're detecting versus any potential further sources of noise or clutter. And then after we're done with that, we can perform an angle FFT to determine the angular position of the object that we're looking at. So how we would do this is we would normally consider however many virtual antennas, and that's dependent on however many receive and transmit antennas we have. But our radar board is structured in a unique way such that we can only consider 8 of the 12 potential virtual antennas. And we have to perform a slightly more complicated 2-dimensional FFT that will give us information related to elevation as well as our normal azimuthal angle position. And then once this step is done, we can then reformat our data and then send it over to the GUI for visual analysis.
All right. Next, I'm going to touch briefly on our course model synchronization method and how it's ultimately going to enable us to perform our data fusion. All right, our course level synchronization method actually uses a local area network connection that sends and mirrors the same commands to devices that control separate radars. In that case, it will significantly decrease the delay between the radars to milliseconds level. And in that case, it will have no frame offset. At the same frame level, we can see that our radar node 2 and radar node 1 are related by some distance and angles. Using the relative position and relative angle, we can actually transform the perspective of the second radar back to the perspective of the first radar and just simply overlay them to create a bird's eye view. We just need to take the location of the objects detected by the second radar and times the inverse of the rotation matrix and also add the XY shift, then it will be transformed back to radar node 1 perspective. How do we know that our algorithm actually works? We need to perform some special test cases to validate our idea. In this case, we have the coordinate test, where we have our bushes and cars on a corner, and each radar can only see part of the trajectory, where the person or the object is moving toward or away from them before or after they pass the corner. In that case, when we overlay the views, we can see both radars can see the total trajectory or path of the whole scene setup. That the purpose of this test case or even the whole project is for drivers to have much more time to react to any situation that might arise during their driving.
Yeah, so here we can see that, if you want to play the videos. So here we can see an example of the corner case. So we see Justin is running around the corner, and Alina just came from around the corner. And we couldn't see Alina before, but now we can. And vice versa, we're here, so we couldn't see Justin, but now we see him, and now we cannot see Alina, but before we could. Yeah, so here is all of the data that we collected and put through all of Sean's code and put into the GUI. So we can see here we have radar 1's perspective, and we have radar 2's perspective. And then when we fuse them together down here, you can see that they're both from the perspective of radar 1. And these green dots correspond with what can be seen in radar 2. And then the red dots are correspond with what's seen by radar 1. And yeah, so we can see that this radar right here cannot see any of these objects over here. But the second that we fuse them together, now all of a sudden it can see everything that this radar saw, and it can see everything that its own radar saw. So yeah, so we get both the views of
of Olena and Justin. And if we go to the next slide. So and now we can perform just regular old object tracking on it, where we have just all the observations that these radars have made. Now we can apply column filters so that now we go from just X and Y coordinates of these observations to actual objects that can be put into algorithms to help with car braking or stopping. So yeah, really helpful.
So in addition to the coarse wireless synchronization system that we have demonstrated so far, our team is also working on laying the foundation for future synchronization technologies that will achieve a fine level synchronization on a nanosecond scale. To do those, the reason we're trying to do this is because we want to take advantage of cross-radar signals, which in essence are just signals that are transmitted from one radar node but received on a different radar. And still containing meaningful information. By realizing cross-radar signal communication between radar nodes, we would allow for raw data fusion of the radio frequency signals instead of having just the point cloud data being fused in post-processing. This will increase the spatial diversity of the downrange profiles of detected objects, as well as improve the overall cross-range resolution of the entire system. Moreover, we will be able to perform joint detection that will be more reliable in noisy environments. But the requirement for such a system is that you need to have an impeccable synchronization of the transmitted signals. And so that's a lot more challenging to achieve wirelessly. So our team has proposed the method of using dedicated precursor signals that will be transmitted before the data collection signals to achieve synchronization. It will use this technique called the idle time sweep. So the idle time here refers to the downtime in between chirp ramps shown in the figure. By configuring them to be slightly different for different radar nodes, what we can do is reliably create periodic alignments of the chirp ramps demonstrated by the rectangle box over there. So these alignments would actually generate what we call ghost objects in our signal processing chain. So ghost objects are essentially phenomenons of partially coherent interference. This means that we have multiple chirp signals arriving at the receivers at the same time. However, because they're different devices, so they will have a slight mismatch in the chirp parameters, such as the chirp slope and the chirp duration, and also because of multiple different reflections, they would have they will be in the presence of phase noise. This would cause the energy of the ghost object detection to spread across the Doppler domain, as shown here in the 2D Fourier transform map. So the velocity of the ghost object spreads across all velocity bins instead of just a few when compared to a real object. So using software simulation of the chirp signals, we can determine a relationship between the chirp configuration, the timing offsets between the two different radar nodes, as well as the ghost object appearance pattern. From our experiments and this software simulation that we created, we are able to complete some of the groundwork to generate a software model that will allow us to extract the timing offset parameters based off the ghost object appearance parameters, appearance information. So this figure visually demonstrates what our simulation looks like. So a ghost object is appearing when we have the interferer signal from a different radar in red, lying in between the originally transmitted signal in blue and the max range object signal in green. And the figure over here shows you how the ghost object would appear periodically from that color pattern. So to summarize, here's a flow chart of our future vision for this ghost object-based synchronization technique. So first, we will send out the dedicated synchronization signal precursors, which will reliably generate ghost objects. And then we would use our ghost object detection algorithm to record all the relevant information of the occurrence, including which frame it occurs at, what chirp, and the range distance of the ghost object. And then this will be fed into our parameter extraction engine, where using the simulation that I mentioned just before, which would allow us to determine what is the frame difference or the initial offset between the two radars. And if we do this fast enough, then we will be able to make real-time corrections to these parameters, allowing us to achieve a fine level synchronization. So that is all that we have. We want to thank our Professor Brockwalter and Professor Madhav for the guidance in the project, as well as some of the grad students, including Lalifa and Ahmed. And I also like to find our funding sponsor, ITC. Thank you.
Any questions?
Great job, that was fantastic. So in the pictures you showed, the notion of time is not there. You didn't talk about synchronization until the end, but if you think about, I mean, do you have cases where you can kind of show an animation of as you turn the corner and suddenly they're no longer both looking at it, and you try to track a particular object over time? But I'm thinking about like safety, original goal, all that kind of stuff.
Right, so our GUI, just to help with the visualization, is we just plot all of the points all at once.
Sure.
But yes, when you actually pull up the GUI and if you hit run on it, you can see the plots, the points start to generate as the time goes on.
Yeah, this is definitely an overlook on our part. We have the ability to generate an animation, but we just somehow totally got lost. Yeah. Yeah.
I believe you that you have it. That's great. But when you talked about synchronization at the end, I wondered at some point there will be some, some error in exactly synchronizing the notion of the time, I guess. So.
Well, for this course level synchronization, the synchronization time frame is like around 1 millisecond delays or noise, and our entire frames to provide relevant information is like around 30 milliseconds. So it wouldn't cause like any problems in the course level. On the fine level, definitely it can create problems, and without a proper synchronization, you wouldn't be able to get meaningful detections. You'll get a lot of noise and scatter, but that's what we're trying to solve.
And then lastly, you guys threw out the idea of using a Kalman filter. So we're just wondering, in order to track things. So if the two people are running by each other, are you sure you're still tracking the one you thought you were tracking? And maybe it's not important. And then what is the model of Kalman filter? Is there just a sense that the velocity will, like, the point has an acceleration? I don't know. Just briefly.
Yeah, so I mean, that's a little bit beyond the scope of our research, but we found a really great open source Kalman filter implementation, and that's what we were using. And really, just all the inputs that we were able to generate from our code very easily fit into their code. So yeah, we did not implement any Kalman filters ourselves, but everything that we made will be able to extract.
Yeah, that was integrated.
I have one quick question. So just out of curiosity, what's the bandwidth of the chirp signal?
So yeah, it starts at 77 gigahertz and goes all the way to 84. So we can actually do 81 or 82. So it's 4 to 5 gigahertz depending on what we need.
And what was the chirp rate?
The chirp rate. So typically for reliable detection, you want a lot of samples to make sure that you actually get the frequency difference correctly and accurately. We tend to use around 60 microseconds for the chirp round duration. That gives us a for sure accuracy in terms of object detection with really good resolution. It also fits for our max range because there are certain hardware limitations such as the ADC sampling rates, and like what we can handle. So yeah, so that's like the number we optimize for.
So that's from the beginning of one chirp to the beginning of the next chirp?
No, that is the duration of one chirp. The idle time would have to be added to that.
Okay. And is the idle time on the same order as the chirp time? Or
the idle time is roughly around 7 microseconds. Yeah, and then we manually tune that for the ghost object generations, but for course synchronization, we can have them all be the same.
Yeah.
Yeah, and then in terms of how many chirps we generally have per frame, we decided to settle around 64 to 128.
So per frame, what's the frame?
So frame of data corresponds to so when we're taking samples, when we see how many samples we want to we have however many frames of data, and then each frame consists of a certain number of ADC samples that we capture, as well as a certain number of chirps that we send, so that we can accurately resolve information related to velocity. And and a frame is like a larger period of time, and then a chirp duration is on a small scale.
Frame is a, yeah,
Yeah.
temporal
Yeah,
idea.
yeah.
Or higher level,
Yeah.
So
And then we have, yeah, and then we have multiple chirps within that, because like I said earlier, we want to be able to help resolve information related to the loss and any other things that we can't know if we limit ourselves to chirps.
Typically, our frames will consist around 130 chirps.
All right, I guess we'll get started. Thank you everyone for attending our capstone presentation. My name is Christian. For the past year, I've had the pleasure of working with my group mates, Gary, David, Roberto, and of course, my dear Terrence. So here at HortaBeam, we're trying to develop a new approach to grow plants using laser diodes. In other words, we're trying to reinvent the sun. You see, there's a crisis that the horticulture industry is facing right now. The projected population is reaching around 9.3 billion people by the year 2050. And so the United Nations has deemed it necessary to increase crop production by 60 to 70% by then. So what solutions do we have? Well, we have vertical farming. Essentially, you create a farm indoors and you make an efficient use of space by layering them upwards in a vertical fashion. Now, traditionally, lighting systems that we've used for this version of farming have been fluorescent bulbs or high-pressure sodium lamps. And they're really nice because they replicate the sun's light. But more recently, the novel technique to light plants is LEDs. And this is because they allow for narrow spectrums. Plants don't actually need the entire spectrum of sunlight. They only need a few at red and blue. And so we introduced a new way to grow plants using lasers. And you might be wondering, what makes lasers so much better? Well, for LEDs, you need on-site circuitry to actually power or deliver light to the plants. And due to the close proximity of the circuitry, it's going to be creating heat really close to the plants. And this is really bad news because it takes more energy and essentially it makes it a more hassle to grow plants. Lasers, we can put a laser really far away from the source or really far away from the system, and it can deliver the same amount of power and at a much less costly heat. And in turn, we're expecting to use less energy to regulate the temperature around the plants, and we want to induce more growth. So here's a high-level block diagram of our system. It looks like a lot right now, but don't worry. We're going to go through it as we go on the presentation. The main idea here is that we have one beam from a laser diode, and we're going to transform it into multiple beams throughout the system. And this will contain multiple chambers. For our case, we're using 4 chambers, so we need 1 beam to 4 beams. We use a network of beam splitters to split the beam into 4. And eventually it reaches the diffuser where it will go to the plants.
So based on our high-level diagram, we have our official laser-based horticultural lighting system design. Just as planned, we have reached our goal of implementing a 2-layer poly design as our major plants growing shelf. So as you can see, on each layer, there will be 2 plants or 2 growing chambers. So in total, the system can supply 4 plants. And as you probably noticed already, we have many different colorful boxes. These are our own customized 3D printed parts that are basically plastic box used to hold our lens. That we have 3 different uniques. We have 3 uniques design that are the mirror box that basically does the reflection job of a laser beam. And also we have a beam splitter box that is basically the same as the mirror box. Only we replace the mirror with a beam splitter. And as Christian mentioned before, the beam splitter basically also does the reflection job and also a transmission job. So basically with this, we can split our single beam into multiple beams. And with our last components, the customized 3D printed components is the diffuser combination box. This structure has a mirror and a diffuser in it, which completes the final process of diffusing the lights onto the 4 plants individually. And throughout our course, constantly disclosing and completing this physical system, we also want to characterize our system, and more importantly, to characterize our laser input and our system output, which is the PBFD light. And for the sake of safety in our labs, we only chose a low-powered laser that goes only up to 3 watts. And we are then super interested in how a higher powered laser system would have similar behavior as a lower power system. So we can get into more details about the system component. So now I'm going to take the next couple of slides to discuss a little bit more detail about the components in our system. So the first component I'd like to talk about is our source of light. Our light source is a high-powered laser diode that emits light at a wavelength of fixed 450 nanometer wavelength, which is also known as blue light. And it has a controllable optical power output between 1 and 3 watts. The next component is the beam splitter lens. Its purpose is to split the incident beam into 2 equivalent laser beams that are both half the power of the original beam. But these lenses also help us implement the design of the multi-layer and multi-chamber into our system. Next up are the servo holders. So these are important because they allow us to properly and consistently align our lenses throughout our the laser beam throughout our optical system. These servo motors are controlled using an Arduino, and they allow us to rotate the lenses in increments of 1 degree. And here's a demonstration of the alignment taking place. And these servo motors are found in some beam splitter and some mirror boxes. So next up is the diffuser lens. The purpose of the diffuser lens is to scatter the narrow laser beam into an optical cone shape, which is more suitable for growing plants. And these specific diffuser lenses have a diffusing angle of 60 degrees. So the main instrument that we use to take measurements for our project is the PPFD meter and sensor. PPFD stands for photosynthetic photon flux density. And what this measures is how many photons fall onto the surface per second. This is the most common measure that is used in the horticulture industry, and it's used to compare different growth lights. This specific meter, it allows us to manually and automatically log our data so that we can use it for later analysis. Finally, the last component I'd like to talk about is the automatic grid. So this grid allows us to take measurements of PPFD with a meter at consistent locations throughout the grid. It's controlled using the language of G code, and we take the measurements across a 5x5 array. And here's a visual representation of it in action. And with the help of the automatic of this automatic grid or XY plane, we can have our full power measurement process. So basically, so ideally, what we are expecting at the output is the perfectly Gaussian distributed diffuse light. And within our 5x5 grid, it's gonna appear into like this ideal Gaussian shape. And further into our measurements, we are particularly curious about the 3 major parameters. First is the input voltage of our laser diode. And second is the source distance, that is basically how far our laser diode is from our full system. And third, the diffuser height, that is basically how high we have basically the height of the diffuser and the plants. And Gary is now going to talk about the results.
Just like what Terry talked about, the 3 major parameters, there's a reason that we we are interested in these things. So first, since farmers will want to change in the diffuser height accordingly to the plan, we want to study how will the diffuser height affect the system. And second, since one main advantage of laser system over the LED system is that it reduces the on-site heat accumulation. We want to study how will the source distance affect system. And since our system is aimed to actually grow up plant, we're aiming for a higher power laser. So we want to study the electrical to optical power. So for these sets of graph, we keep the source distance and the electrical power the same. The only thing that we're changing is the diffuser height from 12 inch to 10 inch and 7 inch. So there's two major takeaways from this graph. First is that when we are decreasing the diffuser height, the measurements actually get more centered, and as well as the PPFD reading goes up. This is also true when we are taking other sets of measurements, when we are changing the source distance and also the electrical power. After we are changing these parameters, you may find that when we are changing the source distance, what we expected is that no matter how far we put our source at, the PPFD measurement will be same, but this is not kind of true. You can see it more clearly if we put into a 3D graph. The top layer is that we put the source at 20 inch, and the second layer is that we put the source at the 42 inch. You can see that the one at 42 inch has taken a little bit less PPFD than one that's put at the 21 inch. Our assumption is that when we are put the source far away, the laser beam actually diffuse a little bit before it reaches the system. So, and the third part of our measurement is about the optical power and the electrical power. So you can see on the left side of the graph, this graph, we only have 3 sets of the electrical power to optical power measurements. And the best fit line for this graph is linear. But when we put the 4th set of data to the graph, which consists of a higher electrical power laser, you can see the best fit for the graph is actually a quadratic graph. This means that the electric power to optical power conversion is lower when we increase the electrical power. And David will explain that.
Okay, so after having all the results, the very next thing we wanted to do is to figure out how are the results compared to existing commercialized LED systems. So here we have a commercialized LED system as a PPFD graph on your left, and we have 40 beam. That's the data for one growing chamber, and please do keep in mind that specs like source distance and diffuser height are actually quite different as in the LED system, since the source is put relatively close to the growing site compared to our system. And so we eventually came up with the idea to upscale the electrical power delivered to each basic lighting unit in each system. In our case, it's the growing chamber or a diffuser lens. In their case, it's just the whole unit. The whole thing is the unit. So we eventually upscaled so after upscaling the power, what we have here, we see the PPFD delivered for our system is actually not too bad compared to their result, which the whole team all agree that a laser-based system has its own potential, and considering the fact that more work can be done improving the overall power efficiency of 40 beam. And here we see the distribution of 40 beam compared to a commercialized LED lighting system, and we could tell the distribution is uniform, and which is quite desirable for horticulture purposes. So in conclusion, for 40 beam, we have successfully implemented a multi-level system that can be used for plant growth, and at the same time, the system is fully customizable. The system can be extended both horizontally and vertically which will allow the growers to fully utilize every bit of their growing space. And we have also implemented an automated grid that can help us with data collection and the system characterization. Some challenges would include the multiple loss. We have multiple sources of loss, including the laser source and just simply because of the complexity of our optical system. And another thing is, as previously mentioned by Gary, the laser source we used naturally diffuses as we increase the source distance, which basically means when we move the source further away from the system, the laser naturally diffuses and not all the power is delivered to our system. And another thing could be, another challenge would be, also mentioned by Gary, a single laser unit will eventually hit saturation as we increase the voltage. So both of the challenges the team believed could be improved, substituting our single laser source with an array of lasers. And we all believe that the system could be further improved to have better overall power efficiency and lower energy costs in the future. And here we have a demo video that I want to show everyone.
Here we're aligning one of the using the servo board. And here just the process of us taking measurements from different diffuser heights.
Goes on a bit. All right, and that can
acknowledgement. For 40 beam, we want to acknowledge the help with our sponsors, advisors, and do you want to add any?
Yeah, thank you to all of the people mentioned on this slide for making this project possible. Yeah, thank you.
Thank you. Thank you all.
Worried about any laser safety issues here? Or?
Yes, when we were using the variable, the laser which we can control the optical output power of, we use some safety glasses, and we make sure nobody else is present in the lab because it definitely got hot.
Yeah.
To clarify, those estimates of what you would see with the 100 watts, that was using your quadratic fit from the earlier plot?
No, we're actually assuming a phased laser system. So instead of trying to reach the saturation point of a single laser, we instead implement a bunch of low-powered lasers and to reach that same efficiency.
And the data, other than the scaling being different for the commercial version, was three times the.
For the LED?
Yeah, the data, the plots look similar. Did you guys actually record the data yourselves? Yeah.
Yeah, so this is all of these data points that we took are
for the commercialized one?
Yeah.
This commercialized one was from the data sheet of the LEDs. This is the measurement that they provide.
And so we were able to find the PPFD distribution,
the data for it, and we simply converted it ourselves into a graph. As we
Like
see.
MATLAB and you set the
Yes.
values at those points.
Right.
So that's where the plot.
Right. Oh, that's what you meant. Yeah. Okay.
And then the actual way that you move around to take the measurements, you said you use G code, like a machining type of code.
Mhm.
What was the setup that you used? Why was it I don't know if you talked about it. I guess you had something similar to a pen plotter that would allow it to run.
So I didn't mention it, but the grid itself is actually designed to be a laser engraver. But we just decided to use it for our own purposes, and we were able to get it to work.
Yes.
Yeah.
It's like we used to be using our own hand with the because we were only able to get the sensor from from an independent organization or something from a company. There's not much we can do to customize it to make our own system or something. So, but we still want to be consistent while recording all the data. And the solution we found is to make at least the sensor need to be in the same position every time. So we came up with the best way to do that is with the stepper motor, which we can make sure that we can just code it and just place it under the chamber we wanna measure and just let it run. Well, the only thing we'll need to do is just click the button and record the data.
Mm-hmm.
Yep.
Any more questions?
Thank you. Thank you. Yeah, it's the old one. Yeah, then I'll talk about agenda. Yeah, okay. Yeah. So hello everyone. We're Team Optical Neural Network, and we consist of Bryson, Kathy, Eamon, Samuel, myself, and Steven. And our sponsor is Dr. Spencer Smith. He will be joining us online through Zoom. And our team name is BAI, stands for Beauty, Aesthetic, and Inspiration. And yeah, let's get started. So before we go into the whole project, I want to run through some of the agenda. So we're starting with the motivation, and then we're going to talk about some insight of our project. Then we're going to talk about the approach of how we're attacking the problem, how reaching our goals, and we'll be showing a demo and what's the realization after project. So what's the improvement that we can do in the future.
All right, so let's go over the motivation first. So whether if it's like autonomous vehicles, like identifying obstacles on the road, or if it's like production lines, monitoring the quality of the final products, they'll require image classifications or neural network. So our traditional convolutional neural network, they're like software based, and they're very, and they cost a lot of energy to operate. So deep learning is like improving, of course, and then computers also improving, but there's also TPUs and GPUs that are constantly making the process faster. But however, this also comes along with a huge, massive increase in computations, and we need to pay the price, and that is energy. So according to this research, by 2025, training a traditional deep neural network to recognize ImageNet images with 95% accuracy would cause the energy leading to the carbon dioxide emission by New York City for a month. So basically, if we were to continue with the silicon-based computing, if we continue with the same model of using the classical convolution neural network, then we will have to pay a huge price to reach the same result. that's why we propose a different solution, and that is optical neural network. So this way, it will not only compute at the speed of light, but also at very low energy consumption. So first, let's go over the differences between our system, optical system, and the traditional silicon system. So optics and light has been in the spotlight for like the past decade, and the reason why is because of the nice properties that it has, and specifically the like what I mentioned earlier, that it can save a lot of energy. So in neural network, a lot of computations are like matrix vector multiplications and additions or dot products, and they cost a lot of energy. And but if we were to use light, then the light propagation and diffraction will take care of all the physics. So and all the computations. So according to this paper that is over here, if we were to use optics, then each multiplication would go all the way down to 1 photon energy, which is around 10 to the negative 19 joules. And if we were to continue with using the electronic processors, each multiplication would cost around 10 to the negative 14 to 10 to the negative 12 joules. So this is why by using this, we can solve a lot of scaling issues, and we can solve a lot of connection issues.
So now we'll quickly go over the traditional convolutional neural network. So in a traditional convolutional neural network, we have an input layer, a convolutional layer, and then a fully connected layer with activation functions and then an output classification. Really what we're focusing on in the optical neural network is the convolutional layer. Traditionally, convolutions are done creating a feature map from the input and multiplying them by some trainable scale values as you continue to train through the network. What we are proposing is using optics in this convolutional layer, doing that by performing the additions and multiplications through optics, mostly in the Fourier domain, which will allow it to be much more energy efficient compared to the silicon traditional convolutional network. Now Stephen will kind of go over this Fourier optics idea and how that works.
Yeah, thanks, Bryson. So as Bryson mentioned, traditionally a lot of image recognition is done through convolution, and then the convolution, there's a famous relationship that tells us that if we want to do convolution in the spatial domain, it is equivalent to do multiplication or modulation in the frequency domain. And so this gives us a nice way to perform convolution, which is in computer, we can just simply perform an FFT, we do some modulation and perform an inverse FFT. But the thing is, the FFT or the Fourier transform, we can do it for free in optics. But for free, I mean, if I just say, let's put a lens right here. So our object will be 1 focal length away from the lens, and exactly 1 focal length on the other side of the lens will be the Fourier plane. So here we'll have the Fourier transform of our object. And similarly, we put another lens in a similar configuration. This lens will be performing an inverse Fourier transform. So if we just do nothing, the total of 4 focal lenses, we call it a 4F system, is simply doing a relay. It's like doing Fourier transform and inverse Fourier transform. So it's like doing nothing. But now we have access to the Fourier plane. We'll be able to perform phase modulation using some optical device called a spatial line modulator. We can modulate the phase domain of this Fourier plane information. So this gives us something different at the image plane, which we can capture using the camera. So together with this Fourier optics concept, we're able to perform convolution optically. And this will form the optical portion of our hybrid system.
So now I'm going to give you a rundown of our design overview, which is the block diagram, the hardware setup of our system. So we're starting with a green laser that acts as our light source. The green laser will shine a light into the digital micromirror device. The digital micromirror device will then pass on to spatial light modulator, then go into camera. The camera will capture the image, send it back to the computer, and the computer will adjust based on the parameters to control the digital micromirror device and the spatial light modulator. The data captured is going to a database, and the database is also there just for the
other half, the software part of our project. So for the convolution layers, the digital micromirror device acts as the input layer, which is used as the image encoding. The spatial light modulator is the hidden layer, which done all of our computations on, and the camera acts as a inference for our project. So for the digital micromirror device, as the name may sound, it's a device consists of many mirrors. It can reflect light, so it can select the patterns we want to use for our later computations. For spatial light modulator, we're going to give you a rundown of how it works. Basically, spatial light modulator functions in phase modulation. As you can see in the image to the left over here, when we are having an incident planar wavefront going to the spatial light modulator, without any voltage applied or anything done with the spatial light modulator, eventually it will give out a reflective planar wavefront. It doesn't do anything. But if we're applying voltage, or say we're applying a phase mask onto the spatial light modulator, then it will create this reflected modulated wavefront because of the bifringence effect of the liquid crystal within the spatial light modulator. So this is the effect we want to eventually have, because in this way we're able to change our phase of the input wave. And this is our whole setup. This is our whole setup. So we're starting with a laser over here. It goes through a linear polarizer, a half-wave plate. Then it goes to 2 mirrors, and then a 4F relay system. The 4F relay system is basically an expansion of the beam. It enlarges the beam onto the digital micromirror device to the bottom right. The digital micromirror device will then pass the light into one of the 2F lens, which transform the spatial image from spatial domain to Fourier domain. The Fourier domain image will then do the convolution with our spatial light modulator. Due to some technical issue, this is not the latest version, so just sorry, bear with that little mistake. With the spatial light modulator, then it passes onto the camera, and before the camera, we have another 2F system just to transform it back into our spatial domain. Therefore, the images can be captured by the camera. And then, next slide, please. So here we're having a little demonstration of our project.
Yeah, so I'm just going to voice over this project. So we're showing the optical portion of our hybrid system. So over here, this is the spatial light modulator. So we have already trained, and then we know a mask, and we have loaded a mask onto this spatial light modulator right here. And then this is the Fourier image. It's quite small, but you can see that. And we pick the data set and we load an image onto this digital micromirror device. So a laser is shined onto the digital micromirror device. And then you can see we have these 2 lenses. One is performing Fourier transform, the other inverse Fourier transform. So we have the Fourier image right here, which is modulated by the spatial light modulator. So the camera can capture an image, and we can compare this convolved image with our original image on our lab computer. So you can see right here. So the left-hand side is we're using a KMS digital data set. It is original image. It's quite hard to see from here, but the right-hand side is the convolved image that's captured by the camera. So, and then we can use this convolved image. We put it into the rest of the neural network, which is purely in software. We add nonlinear layers and fully connected layers to give us a final label prediction. So after that, I'm going to go over quickly the software model. So in our software, we have a model that basically models everything from the optical convolution to the rest of the software layers. So the reason that we want to have this is because we want to be able to collect theoretical results. We can adjust some parameters, and we can know what's expected. We can expect what's going on in the system. And the other thing is we can perform training in the software model. So I'm going to quickly go over the full model, the software model that includes both the optical part and the software silicon part. So in the beginning, we have a pre-processed image. We want to pre-process it because we want to make it monochromatic. We have even if it's a colored image, we'll just turn it into monochromatic, and maybe we'll adjust the size a little bit. This is corresponding to the digital micromirror device in the hardware. After that, in the software, we perform a Fourier transform. we multiply by the phase max of the spatial line modulator and inverse Fourier transform. This gives us a convolved image. And while keeping our pre-processed image the same, we can shuffle through a few different spatial line modulator phase masks and then capture these images sequentially. So essentially, we can get multiple convolutions from the same image. And then this concludes the optical portion of our project. And after the camera captures these images, they'll put it through into the computer, and then they'll apply nonlinear layers like max pooling and ReLU activation. After that, these images will be flattened into a 1D array and then go into some fully connected layers before at the output layer, it gives us a label. So this captures the full hybrid system of our project. So you can see that we only have one convolutional layers. So we also have a software control algorithm, but it's actually pretty straightforward. So for the spatial line modulator, we just want to be able to display a phase mask on there. And digital micromirror device is the same. We want to be able to display an image up there. And the camera, we just want to capture an image. So that's all we need from the software control algorithm.
Okay, so now we're going to go over the results. So we're going to go ahead and see exactly how our system is better. So there are three categories that we're going to look into. The first one is energy consumption, because that's the main advantage of our system. The second one is the accuracy, because at least we want our system to be working. It needs to be able to classify images. And lastly, it's the training time, because we don't want the time to be too long. So first, let's go into the energy consumption. So our system, like what Steven said, it's a hybrid system, which means it composed of it has both a hardware part and a software part. The hardware part is the actual convolution, and the software part is to deal with the non-linearity. So the software part for both our system, hybrid, and the traditional one has the same energy consumption. So we're really just going to look into the difference, which is the hardware part, which is the convolution. So the usual way in silicon computing to do convolution, the brute force way would take n to the 4th power. So the image would be n by n, and n is the number of pixels. So that's what n is. But however, there's FFTs where we do some Fourier transforms and some complex multiplications and some inverse Fourier transform, which is the same thing as a convolution. The way to do that, it will speed up the process. For silicon computing, it will take up to n squared log n, and that is this dependency on n is analyzed through some complex additions and multiplications. So that's how we got that. But however, in optics, everything, all the FFTs will be for free. The Fourier optics that Steven mentioned earlier. However, there is little constant overhead. So for example, we need energy to power up the lasers, the DMD, the spatial line modulator, and the camera. So that's why there's a little overhead over it. And then on the graph on the left, on the right, you can see the plot where the x-axis is the energy in microjoules, and then the y-axis, the x-axis is the image size. So that will be n, which is just the number of pixels for one n by n image. So in the beginning, you see it might be more advantageous to use silicon computing because the image size is very small. But once it reaches a certain threshold, which is around like 400 by 400 pixels of image size, you can see how our hybrid system comes into play and how it saves energy in comparison.
Now we'll quickly go over some results that we got from our model. So here we're going to be comparing our optical neural network model to traditional convolutional neural network model. And here the big thing is that they're analogous, meaning they are both like the same. They have one convolution each. The convolutional neural network has one input and 10 outputs, while the same with the neural network. So we get the most similar and accurate results as possible. And as you can see, the optical neural network may take a little bit longer to converge and get to the point, but the accuracy is pretty similar once it gets there. And that's really what we're looking for. And the big thing is the energy consumption. We might get to the similar accuracy with a little bit more time, but the energy we lose is much less, and that's what we're going for the project. So now another thing we can go through is the use of masks in our project. We decided to use one mask, but we thought, what if we use multiple masks in our system? And the ways you can do that is you can load multiple masks into the spatial light modulator. So through the software model, we tested that. We put multiple masks in, which was pretty easy. We learned that the more masks you use is the higher accuracy you can get. However, the trade-off is it takes a little bit longer. Once we got past 10 masks, it didn't make much of a difference accuracy-wise. So we decided that, you know, if we're trying to test it, the main number of masks you need to use is around 3, because the trade-off from the time is not as much as it lowers the accuracy.
Due to some technical difficulties, the next slide is not. This is not the latest slide. There are several others that was supposed to be put in there, but we didn't. We're just gonna do a voiceover for the other slides that are missing.
Right. So something else we tried in the software model, which made it really easy, was testing amplitude modulation. Most times when you use a spatial light modulator in this project, you would mostly do it in the amplitude modulation mode. It's much easier and intuitive for us to see it when you convolve them together. You can use just a regular low-pass filter, and the output looks very similar to the input. However, when you use phase modulation, when you convolve a phase and a regular input, the output doesn't always look very similar. It's not very intuitive to us. So you would think that the amplitude modulation might get better results. However, when we compared them, we want to appear, but when we compared amplitude modulation, phase modulation, and the software model, they turn out to be the exact same. And the good thing about the phase modulation is we don't waste as much energy using extra lenses to perform amplitude modulation. So that's another reason why in our design we decided to use phase modulation, because when amplitude modulation we had extra lenses that would waste a bunch of energy when it just yielded the same results as phase. So that's another reason why we use the phase modulation in the optical mode of the project.
Now I will just summarize our overall achievements. Like with 1 year's hard work, our group has successfully built this hybrid optical silicon system that enables the deep learning with high accuracy and improve the scalability with lower power energy consumption.
And for future improvements, as you can see earlier with the video, you must see that the images after the, so I think it's somewhere over here. Yeah, you can see the images on the right. It's not that, it's very difficult to read what actually is there. That's one of our improvements in the future, that we're trying to decrease the noise. And because of the noise is adding up throughout the parts, we need to find a way to decrease the noise and trying to increase the visibility of our patterns. And another thing we can do with our software model is to use a cascade convolutional layer, meaning once we're having the convolution done and captured by the camera, we're putting that image back into our optical neural network again to get trained. In that way, it will increase the accuracy of our optical neural network, as well as, it will increase the accuracy of our neural network. And just acknowledgement, we want to thank everyone that helped along the way. A big thanks to our sponsor, Professor Smith, with all the big help, and the postdoc, Dr. Che Han, for helping us along the way, and especially to Dr. Reza and Michael, just for everything. Yeah, thank you. Is there any questions?
Yeah, one of the things that's in your loop is the camera, right?
Yeah.
So as things, like you said, in the future, when you have a lot of computation, you want to do it really fast. That means that the camera needs to operate faster and faster and faster. And the camera consumption, the power consumption is pretty much exponentially goes up when the camera runs from 30 to 60 to 90 to 120 frames per second. That, I don't know if you accounted for when you compare the power.
Well, in our project, the parameters we used is, the bottleneck is basically our spatial light modulator and our digital micromirror device. Both of them runs at 60 hertz, and the camera runs at 165 hertz. And the power consumption we calculated and we plotted in our slides is basically based on that. So the camera in our project isn't the bottleneck. So,
but eventually, I mean,
yes, eventually it will scale up.
Scale, right?
Yeah.
The other thing is also when the camera runs faster and faster and faster, because your frame rate is higher, the amount of time the camera gets to collect the light, becomes shorter and shorter and shorter, which means that your images now, will not be as accurate as it is at 120. It will be like
Yeah,
240
yes,
or 500
exactly.
or 700. So
Yeah, so as we shorten the shutter time of the camera, so in general we should be fine, but in the limit that it's get extremely small, we don't want like the quantum mechanical effect of the optical laser to kick in. So as long as there's we can refer to a paper, but as long as we have some reasonable number, like we only need a few photons per pixel to give us like a reasonable result. So if we still use that, then that still give us like a reasonable result, because in machine learning, it doesn't have to be super accurate. So it's like if we want to multiply 4 by 5, in machine learning, if it gives us like a 20.1, in general, we should be fine. So that's what enables us to use like the optical setup. So yeah, we're able to lower the, in principle, we can lower that. Yeah, as long as it like we don't have some quantum mechanical uncertainties in there.
Yeah, just a couple things to clarify. When you showed accuracy, this is the classification of the full train hybrid.
So that's the software model only on that one. So that's not the full, yeah, the software model.
But the software model includes the.
Right.
Yeah, and then on the software model, it seems like you're modeling like the FFTs and all the that would be done optically. It seems like the noise kind of related to what John was saying, like your assumption of like how accurately all of these FFTs are doing and what the real pictures, there's like a certain way, pattern the way that image looks with like the virtual little circles appearing and stuff. I mean, is that part of your software model too? Sort of the assumptions about noise and the camera.
Yeah, so definitely there's some noise in there. So what we did is that we can have a sanity check. So instead of putting down some phase mask on our spatial line modulator, we just put a constant or like basically all 0 in there. So you can imagine that spatial line modulator just acts as a plane mirror. So it's not doing any modulation. In that special case, then the camera captured image, ideally we want it to be exactly the same as the input image. So based on that, we can get like a sense of what's the noise looks like in the system. And the other thing that's kind of we're not expecting is that the spatial line modulator, because I think it's because of the liquid crystal, it shows us like these little speckles that we're seeing on the spatial line modulator, that we're seeing on the camera. So that's still something that we want to solve.
Yeah, what's anytime you've done anything like very funny things like those kind of patterns just from signal processing.
Yes. So yeah, so it's kind of hard to model that. That's why it looks a little bit different. It's something that we can improve on as we continue to work. Yeah. Right.
Yes, please.
So in normal convolution, now you actually have 3 color channels. So the logic you guys have thought about actually taking and splitting the channels into 3 and then deconvolving into separate optical maps, or have you thought like, so I understand you use AMA to this point and into black and white. In real convolution for images, you have to have more. There's a lot more data with a lot more colors. And the question is, when you start separating these things, what's the overhead when you have to do that kind of processing optically? And the other thing that I also want to ask you is that, sure, accuracy doesn't matter for input, but accuracy matters a lot for training. So you're only doing input with optical, correct?
Yeah.
Correct. Yeah.
So when we talk about the colored image, we actually, it's not shown on there, but we tested with some more naturalistic data set like CFAR10, it's like animals and more naturalistic objects. So the easiest way for us to do it is just to convert it to grayscale before we throw it into the optical system. But definitely we will, it's possible for us to passing these, like, let's say RGB channels separately into the system. So we may have different phase maps for these different channels, or we can have them as the same, like we're passing the 3 channels and then we use the same convolutional maps, or we can give it different phase maps. But we can only do it like temporally, so it's like do it sequentially. There's no way for us to do it all together unless we just combine all these channels into one.
See what the performance difference was in that
Yeah. We've tested it out. It's not shown there, but when we combine the 3 channels into one, we definitely lose some information from that original image. So our performance didn't get quite as good as, like, let's say, a regular analogous CNN, because maybe the CNN, it can take in all channels in together and then perform convolutions separately on these channels. So definitely, if we want to optimize it, we may just passing these channels separately, but in general, or just passing the grayscale still give us like a decent amount of accuracy. Yeah.
And any other questions?
Okay, hello everyone, we're MPL, or Massless Projection Lithography, and we're going to show you what we were able to accomplish this year. So what you see here is contact lithography, which is currently used in the market. This is typically used for commercialized products. So what is lithography to begin with? Lithography is the process of shining UV light down onto the substrate to expose a photosensitive material. So typically you see that pink or red layer, that's your PR or your photoresist. So anything that UV light touches gets washed away. So this contact lithography uses what's called a mask, which essentially acts like a stencil to allow UV light to hit the substrate in different areas. This makes exposure time super quick, but the mask has to be manufactured and shipped to the customer. Instead, what we're doing is we're completely removing the mask. So we're replacing this with a projector system. So the projector shines whatever pattern you want down onto the substrate. So what this really does is it allows you to make your process faster, cheaper, and more widely available, because you don't need to produce this mask, which can take up to 4 weeks to make. And when you're iterating designs up to 40 times, this can get extremely expensive and time consuming. So this is great for rapid prototyping. Just as a comparison to what's currently on the market, as I said, contact and stepper are pretty similar. So those are really used in commercialized areas. Direct Rate is another maskless option, but it uses lasers. So it goes pixel by pixel, which can be super, super slow, and it's very expensive.
So now I'm going to talk about how our actual product works. So on the left here, we have a UV projector, which then projects our pattern into a lens, which then focuses the image down onto a substrate, which then exposes the photoresist. And then since we wanted our minimum feature size to be about 100 to 200 microns, we had to shrink down the image. Therefore, any circuit that's bigger than our image, we'd have to expose in multiple instances. So we then snake through a grid, exposing each image at a time, and the chip is moved using actuators to go to each spot on the chip. So now I'm going to talk about an overview of our system and how all the subsystems work together. So first, you input your design and your exposure time into the processor. This then controls our projector itself. So in the projector, it communicates over I2C with the digital light projection controller, which then controls our digital micromirror device. And this is basically an array of thousands of micromirrors, which are controlled individually, and each one essentially corresponds to a single pixel. And then in there, we have a UV LED, which we are powering externally, which then shines into the DMD and reflects through the optic system. The processor then communicates back and forth with our Arduino, which then controls our stepper motors, which moves around the substrate. and the processor and Arduino are communicating to make sure they get the correct times to move our substrate, as well as when to start exposing our image. So now I'm going to talk about how the communication between the processor and Arduino works to get the timing correctly. So first, the processor sends up exposure time and the grid size over to the Arduino. The Arduino then moves into a start position and then sends out the command to start the exposure. So after this command is sent, it tells the processor to start displaying his video. And while this is happening, the Arduino is waiting until the video is done exposing, and then we'll move to the next grid in the snake. So after that, it loops back to the start exposure command and displays the video and waits again until it gets to the last part of the grid. And then after it gets to the last part of the grid, it'll do the final exposure, and then it'll move back to its homing position. So now we have our demo video. So here, the substrate is moving to the homing position, or to the start position, which is where the first exposure happens. And then after it gets there, the UV light turns on, and then it moves to the next part of the grid and displays the next image. And it'll keep doing this. For this example, we did a 3x3 grid just to show it all. And then, so we can see it's moving in a grid and exposing a plus sign at each location, just to so we can show something that's like visibly clear on here.
Yeah, and we ended up using just a piece of wood so that you could see it, because the silicone was a little difficult to see in the video, but we do have an exposed chip for you.
Yeah, then so after it's done exposing the grid, it'll then move back to 0, 0, or the homing position.
All right, so the main input to our processor is going to be an image of the schematic file. So that's going to be at 907 pixels per inch. That's determined by the optical scaling. So that's determined by the placement of the projector and then the lens relative to it. That determines how large our image is overall. So that ends up with about 28 microns per each pixel. So, and because we have a projector resolution, we have a 360p wide projector, that results in an image scaled down to about 1 centimeter by 1.8 centimeters. So then the solution to this is going to be moving the substrate. Well, the solution to the issue of having a larger schematic than this 1.8 by 1.01 centimeters is going to be moving it to a different portion of the substrate and exposing each part at once. So you can see here, this is what it'll look like. This is what the image processing will spit out, just shooting out one image at a time. And it converts these all to videos, which our processor can show much more easier than photos. So yeah.
Yeah, and then we used 2 stepper motors in the X and Y direction to actually stay quicker that Alex just showed you. And we did this by communicating with the processor, which Naral kind of talked about before. So receiving the size of the substrate and exposure time, the steppers are able to move to that start position, snake that grid, and go back home to 0, 0. We ended up micro-stepping, which allowed us to have like really smooth movement, which meant that the chip wasn't moving around a lot on our stage. And we ended up using closed loop feedback with this little driver you see here, PID control, in order to get it as accurate as possible. So a few of the challenges we ran into here, we're getting the exact image size from testing so that we could align as best as we could. Obviously, just looking at an image visually, you can't really measure how big it is. So we had to go into the clean room, test a bunch, figure out how big our feature sizes were, and kind of go back and forth until we found the right alignment. Another issue we ran into was factoring in delays of the processor. So the processor takes a little bit of time to boot up, and the Arduino had to factor that in before it started moving. And then another issue was the fact that the function for the stepper motors could only take integer values. So that lowered our resolution to about 3.125 microns per step. Still really great, but you can kind of see in some of the pictures we'll show you later that there's a little bit of wiggle room.
So a number of modifications needed to be made to the projector to support UV LED exposure. And so first we soldered the UV LEDs onto the flex cable that came with the projector itself. But then we realized that the projector board wasn't able to support or provide enough power to turn on the LEDs. So we are powering them externally by a different source. And then we also ran into the problem that the DMDs on the projector don't work unless there is a flex cable drawing current. And so we kept the RGB LEDs plugged into the board and just attached external heat sinks and electrical tape to make sure that none of the light would leak through. And then also we removed the wavelength filters inside of the optical engine in the projector in order to maximize the optical power density that was provided by the UV LEDs. And finally, thermal paste was added between the heatsink and the UV LEDs to prevent the UV LEDs from overheating, because we did have problems with those LEDs damaging the flex cable that came with the projector. And so all of these modifications required a lot of trial and error, because we didn't have documentation that really went into depth about the individual components of the projector. And so the optical system uses one double convex lens that is 50 millimeters diameter and 50 millimeter focal length. And the lens is 2.2 centimeters from the projector lens, and the substrate is placed 4.05 centimeters from the lens. And so we get a final image size of 1.81 by 1.01 centimeters. And that gives us a minimum feature size limit of 28.3 microns. And we'll see later on that that is not the practical minimum feature size that we got during testing, but this is the limit that's set by the optical system itself.
So you can see this is a close-up of the working stage. So you can fit about 1 by 1 inch substrate up to 5 by 5 inch substrate. If you wanted to go larger or smaller, it'd be somewhat reasonable, but not really necessary. Then this is the projector and lens mount. The projector and the lens mount are held together by a plate, which is then mounted using T-slot rails over our actuator system. You can see down here, this is the actuator stage. This is our XY stage that supports the substrate platform. And then our lens and projector are suspended over those. So those are fixed, and then the stage will move around underneath it.
Yeah, so to test all these things, we had to do a lot of testing in the teaching clean room. And we tried several different types of photoresist, but we ended up using liquid photoresist because it was easy to test and quick to expose. And we found that the 50-second exposure time worked best for us. And here you can see 2 different mask images that we tested with. And then on the right side is a 2x2 grid of the mask. So you can see the alignment there. And in this first one, you can see the alignment is pretty good, but you can see in some of the rectangles that it's curved a little bit. And that's due to the curvature of the lens, which gave us some trouble. We couldn't do much about that. But you can see in this one, this image was not in full screen. So the curvature of the lens didn't have as much of an effect. You can see that the edges are a lot more straight here. And here are some close-up images of the alignment. In that first image there, it's one exposed rectangle on the left side, and then the actuator moved the substrate to the right. So it was supposed to move directly to the right, but you can see that it's shifted upward a little bit. And then same thing there in the second image. It was supposed to, so there's one exposed rectangle on the top, and then it was supposed to move directly down, but it is shifted to the right a little bit. And then in this third image, it's just some small details in one of the mask images that we tested. And yeah, so we decided that our minimum feature size would be 150 microns.
Yeah, so here we just want to summarize our total expenses that we've gone through throughout the year. So we went roughly into $1,000 that just went into the product itself, as opposed to roughly $1,800 that was spent in total for everything that we've ended up using to test the product itself. And that was out of just an original budget of $3,800. So you could pretty much tell that it is pretty not too costly. And yeah. Thank you very much. And are there any questions?
Also, we're able to expose our logo in the past couple days. So if they weren't on the slide, but you can kind of take a look here. If you guys want to see it later, feel free to ask us if we show it to you.
Terrific. There's so much you had to integrate. It sounds like a big part of it was the mechanical alignment versus optical. You had to make sure that the axes are lined up perfectly, and then the curvature that you talked about. You did a really good job of identifying all that. I don't know, if you had more time, are there ways that you would address that, or would you try to reduce the trade-offs and how big an area to move? Any comments?
I mean, there's a lot more stuff we could have done. So in an effort to save time, we probably would have just tried to reduce the image size if we're trying to make it very accurate. Just to reduce the image size, like the central portion of the image, so that we can maintain like the integrity of those lines in a very quick and cost-effective manner. Because there's a lot that went into this project, and there's a lot more we could do. So that's not really our top priority per se.
Yeah. So you had another person, like seems like you need like a process to calibrate, what this step would be. Ideas on that? Like how did you align things? What was your process to try to make sure the x-axis for mechanical stuff matched?
It was basically taking that that square plus pattern. We would align it, or we would expose one image, move the actuators over, expose another image, and then just look at it really closely in a microscope and say, the top and bottom are off by, like one time it was off by 150 microns vertically when we were just moving horizontally. So then we knew that's a rotational issue. So then we moved one of the legs of the supports. We moved it by 6 millimeters to get that more accurate. And then making sure that the horizontal alignment lined up. We actually saw the results of that with those two side-by-side rectangles. We would do the same thing and then look at the distance between those features, and then go into the actuator controls and say it needs to take like 4 more steps, or however many more steps it needs to take to make up those last few microns.
And is that a process that you could, with this hardware, would it be possible to keep getting better and better, or at some point would you need a different hardware approach to get it more?
Emily mentioned the 3 micron resolution for the actuators. That's just due to that's what 1 step is on the actuators. So that's
you never get better.
Yeah, we're not getting much better than that. But since our feature size is around 100 microns, we're gonna call that pretty good for now. We could definitely get better stepper motors, better actuators, better stepper motors. We could mechanically scale that down. So if we had some sort of gear system, like some sort of mechanical scaling, we could get it down below that. But
yeah, similarly to the previous group, we pulled this off of a laser printer, so we could definitely improve on the stepper motors. Also adding like a Z stage, I think would be really helpful to automate more. And then on top of that, just further improvements would be, we're using a really low resolution projector right now, and that was just purely based off of cost in the beginning. So I think if we upped that, then our project improved a lot in terms of feature sizes.
Yeah, also we mentioned a 50-second exposure time. For reference, the mask system in the lab is about 12.5 seconds. So our exposure time is about 4 times as much, but we only are testing this with 1 LED. So if we include 2 LEDs, then we're only 2 times as much. And then if we go up in size, we may get we'll either get a higher optical power or we'll get higher resolution. So either of those are going to be very good for our project.
Thanks so much, and I hope you guys made one of those cool logos for everybody on the team. It's really nice.
Okay, wait, that's clutch. It's just the top.
Yeah.
Use that. Oh, I can just flip the sides too.
All right, how's it going, everybody? For the last presentation of the day, thanks for coming out. So yeah, we are the group representing HGH USA, and we're here to introduce our infrared calibration source. So we all live in a world where important decisions are made about our loved ones, and they're based on the measurement of a single device. So there's a wide variety of infrared handheld thermometers and thermal imaging cameras that are used in doctors' offices every day. And the caveat about these devices is that they require continual upkeep when their warranties expire. So how do we go about that, right? So in a doctor's office, they might point an infrared camera at you, and there might be a little bit of discrepancy. And so we offer a precise temperature source where it can be in constant view of an infrared device. And we essentially reduce the error in infrared imaging devices. So moving on, a little bit about how our project works. A user will put in a desired temperature input, and the microcontroller will then take that and send a signal to the adjustable voltage source. And that PWM signal will dictate how much voltage goes to our main heating and cooling element. The H bridge over here dictates the polarity that goes into the heating element. And based on the direction of the current, our heating element will either heat up or cool down. From there, our temperature sensor PCB that we designed will read the temperature from our heating or cooling element and convert that into a voltage that the microcontroller can read. This is the basic feedback loop, and this will repeat many, many times until we reach our desired temperature. And to describe a little bit about how this works, I'm going to pass it off to my teammate Zane, and he's going to talk about our team dynamic.
So to implement some of the features that Blake talked about, we decided to kind of split into 3 sub-teams. This was done mainly so we could kind of be most efficient when we're designing and developing our power delivery PCB, our temperature sensing PCB, and then the software that ties all that together. So after we kind of completed those subcomponents, we got together, worked on integration, making sure that all the PCBs work well together and that our overall system works well. One of the reasons why we went with this kind of approach, we could have just gone with an off-the-shelf component for a lot of these functionalities, but the thing is that the previous model, the previous group that worked on this project, they actually tried doing that. But as you can see on this graph to the right, we have this red line, which is the set point temperature of 55 degrees. And even after 10 minutes, it is still fluctuating and getting as big of a variation as 1 degree Celsius off. This was mainly because of a few reasons. One was they used a faulty PID hardware that was just really noisy and didn't do that well. Second of all, they also directly powered our heating and cooling element with a PWM pulses, basically pulsing that cooler instead of what our approach is, which is using an adjustable voltage source that basically can just step the voltage up and down and give that flat DC response.
So now I'd like to talk a little bit about the accomplishments of the power control team. Specifically, I'll talk about the adjustable voltage source that's providing those clean DC signals that Zane just mentioned, as well as the heating element to describe how exactly this product will heat up or cool down at set temperature. So the heating element we're using is what's known as a Peltier cooler. Basically, how it works is you have two semiconductors in there that have a wire coming out of each of them, and based on the direction of current going through the semiconductor through the wires, that front plate of the Peltier cooler, where the temperature is being emitted, will either heat up or cool down. So in our project, we had to control whether the power and the current being delivered to a cooler was, that we had to control the direction it was going. And so we used a circuit known as an H-bridge. Essentially what it is 4 switches. We use transistors to implement these switches in this sort of H configuration. So in one configuration, one is connected to power and one is connected to ground, and then you can switch between them to control whether it's heating up or cooling down. And to control how much and to what temperature that the cooler reaches, we had to make an adjustable voltage source, which we implemented using a buck converter. The way this works is it'll take a PWM signal, and instead of pulsing the cooler directly, that signal will be converted into a clean DC voltage. So that way our microcontroller can read the current temperature and say, we're this much off, let's change the duty ratio of the PWM to this circuit, and that'll change the output level of the voltage, which will then change the output level of the temperature. And doing this instead of direct PWM, so if we have a clean signal, the temperature, the Peltier cooler will, if we're doing direct PWM, you're going from 12 volts to 0 volts, so the cooler will heat up, at a certain point and cool down very quickly. That's why we're seeing a lot of noise like that. But this way, with just one constant signal, we can just reach one constant temperature level. And so now I'll show you a quick demo video of our buck converter, and you can see just how clean that signal is. This shows that by changing the duty ratio of the PWM signal to the buck converter, the voltage increases, and we get a very clean signal. You can see, well, it's a little hard to see in the video, but we're getting about 56 millivolts of ripple at 12 volts. So that's much better going, from 56 millivolts peak to peak from 0 to 12. And we're getting a much cleaner temperature reading.
The next major component of our product is going to be the temperature sensing board. So this is a custom PCB that we created that converts our temperature measurements into a digital voltage that our microprocessor can read and use this information to compare it with the user input. This allows you to generate a feedback loop that adjusts the voltage being applied to the Peltier cooler and change the temperature of the device. So for our temperature sensing element, we use something called an RTD, which stands for a resistance temperature detector. And how this works is its resistance changes as a function of its of the temperature of its environment. And the exact model we're using is displayed in the bottom right of our plot. And it's a 3-wire PT100. 3-wire just refers to the number of leads it has. This offers a higher degree of accuracy compared to a 2-wire configuration. And PT stands for the element that the probe is composed of, which is platinum. And 100 is the theoretical resistance at a temperature of 0 degrees Celsius. Now, our device is designed to operate between 0 and 100 degrees Celsius. And the benefit of our RTD is that it has a relatively linear relationship between resistance and temperature. So what we did was we measured the resistance of our RTD at 10-degree increments from 0 to 100. And this allowed us to generate a lookup table that allows us to convert easily between resistance and temperature. And in order to measure the resistance of our RTD, we applied a 1 milliamp bias current through the RTD, and this voltage drop across this device is fed into a 24-bit ADC, and then our microprocessor reads this, converts it back into resistance using Ohm's law, and then converts that into temperature, which we use in order to create our feedback loop.
So now I'll be talking about our PID controller that we implemented. So on the right-hand side or on the left-hand side is the reference point, which is set by the user on the user interface, and that set point is compared with the current reading of the temperature board with the PRT, and then that error between the set point and the current reading goes into our PID controller in the middle. And our PID controller, we would adjust our KI, KP, and KD values. And at the end, we add up our PI, and D values, which sets the voltage flowing into our Peltier cooler, and this helps heat up or cool it down. So this is an example of like a PID routine. It's not our actual experiment since we weren't able to like actually implement it, but it's like a simulation of how the output response would be. I changed the KP, KI, and KD values. A popular tuning method for KP, KI, and KD is like the Ziegler-Nichols method. So you just start off with a proportional gain, and then you keep the I and the integral and derivative terms at 0. And then once you find your maximum proportional gain, you tune the KI and KD values, the KI for steady state error if you have any, and the derivative term for like oscillations.
So to test the heating and cooling capabilities of our Peltier cooler, we performed 2 tests at room temperature. What we did was we hooked a power supply directly to our Peltier cooler, and the Peltier cooler is rated for a maximum voltage of 12 volts and 5 amps. To play it safe, we limited our power supply to 11 volts and 4 amps. And cooling from around room temperature, which is 22 degrees, to 0.02 degrees, took around 11 volts and 3.7 amps, while the heating process was a little bit easier in terms of power requirements, needing only 11 volts and 2.7 amps. And these are the graphs that we created from our cooling and heating tests. This shows the relationship between the input power to the device versus the temperature of it. And the general takeaway is the higher power that you feed into the device, the faster the rate of change of the temperature. Another relationship between power and temperature is the fact that sometimes it plateaus depending on the amount of power being fed, since heat is also dissipated or added based off of the difference between the device temperature and the ambient temperature.
So now we'll show like an overview of our functionality of the system, which includes our touchscreen, the temperature board, and the Jetson Nano, the microcontroller. So on the touchscreen, you can see the current reading temperature. There's also like a text box entry, which you can like change with the button arrows, or if you click on the text box, a number pad shows up. And I'm just like testing it out on the device to see the temperature go down. I don't know if you can see it later in the video, but once it like reaches around 20 degrees Celsius, from the bottom, it'll stay stabilizing. They'll say stabilizing since that's the set point temperature. But yeah. And also you can change like the units to Fahrenheit. Click on the menu top over here. I didn't show it.
So to sum it all up, this is essentially a really attractive device for any of our partners in the infrared industry. Anyone who uses anything involving heat-seeking algorithms, heat or thermal cameras, infrared thermal devices will use this at some point in their career because they'll need something, a precise known source that it gives the true temperature, because there's always going to be a little bit of discrepancy. So in the example of a doctor's office, it's a pretty alarming situation when they might be using devices that haven't been calibrated in over a year. So a simple solution is that our final product could just be positioned in a doctor's office, they could point their infrared device at this, at our product, and they could confidently make decisions using the temperature reading plus the bias correction so that no child's fever is ever going to go untreated because of a bad read from a cheap thermometer. And that concludes our presentation. Thank you.
So did you say that the PID loop, you simulated it, but it didn't get it working, or?
Yeah, we couldn't implement it in our hardware. We had a problem with the power board. So we weren't able to do that then. But we do have like the code written up for the PID routine. And it's in C++, so.
The power board being the driver that's run by
Yeah, we can bring it back sort of to the beginning. So we have two custom PCBs, and we have adjustable voltage source right here, which kind of highlights just how the power gets distributed. But this is also a power controlled PCB that essentially distributes power to every single component in the system. And so we had everything working kind of separately. And then once we integrated it, we actually had one small component fail that had a giant current surge essentially. And we weren't able to actually do the PID routine at that point. So then,
The system that you're controlling is just modeled as like if the temperature changes like a first order. Like how would you describe the control the model? You put in voltage which is trying to change the Peltier cool.
So we don't end up actually modeling the system. So we use like PID just because it's difficult to find a transfer function or a state space model that could really characterize the relationship between the RTD, the Peltier cooler, and all the in-between devices. So in the example that we showed, we just had a simple first order transfer function, and that was just to illustrate how different coefficients in a PID routine can affect the closed loop response.
Do you expect the real system would be much more complicated?
I believe so, yes.
Pretty non-linear, weird. Behave very differently for heating and cooling.
This is already it's the second time. Yeah, what are your notes? You know, 3 things you'd say to the team. Someone takes it next year, maybe.
Well, I definitely say because I think it was a learning process for us, learning like how to design and like manufacture. Not we didn't manufacture ourselves, but getting the manufacturer like PCBs. I think one thing I definitely learned was that read all of your data sheet because there's always something hidden there that you don't realize will get you. So like I did like 3 revisions of the temperature board before like it got right because there was certain pins that need to be connected that weren't connected or certain things that I hadn't taken account of originally. But yeah. And then same with like making sure everything is rated properly for the amp and voltages that you need to be using.
Do you have an idea about the